Have you ever stood outside on a clear night, looked up at the stars, and felt that profound sense of wonder mixed with something deeper, a quiet, humbling realization that what you're seeing is only the smallest glimpse of what's truly out there? For every point of light shimmering in that vast darkness, there are countless mysteries hiding just beyond our sight, cosmic secrets that defy everything we think we know about reality itself. The universe is filled with phenomena so strange, so beautifully baffling, that they stretch the limits of human imagination, from regions where gravity twists time and space into knots, to invisible forces guiding the motion of galaxies, to signals from the depths of space that arrive without explanation. These aren't just unanswered questions, they are doorways, each one inviting us to step into the unknown and see the cosmos not as a static picture, but as a living, evolving story we are only beginning to read. In this video, we're setting out on a journey to explore 30 of the most captivating and mysterious realms in the universe. We'll travel from the ghostly influence of dark matter, the unseen architecture of the cosmos, to planets that wander alone through the void, untethered to any star. We'll confront enigmas like fast radio bursts, brief cosmic screams that cross billions of light years in the blink of an eye, and black holes where the laws of physics as we know them seem to break down entirely. Each of these mysteries represents a frontier not just of science but of human curiosity. They challenge us, they inspire us, and in many ways they define us as a species bold enough to look into the darkness and ask, what's out there? By the end of our journey together, you won't just have a deeper understanding of these cosmic puzzles, you'll feel why they matter. Unlocking these secrets could reshape technology, philosophy, and our very place in the universe. It could reveal new laws of physics, new possibilities for life, and new chapters in the story of everything. So whether you're new to the wonders of space or you've been gazing up your whole life, you're in the right place. Sit back, open your mind, and let's venture into the great unknown together. What truly defines a cosmic mystery isn't simply a question we haven't answered yet. It's a profound gap in our understanding that hints at realities and physics we haven't even begun to imagine. These aren't minor puzzles with neat solutions waiting in a textbook. They are fundamental cracks in the foundation of our knowledge, suggesting that the universe operates on principles far stranger and more wonderful than our current models allow. Think of them as the deepest riddles of existence, where every new piece of data we manage to gather often leads not to a satisfying answer, but to a dozen new, even more perplexing questions. This is the essence of exploration at the cosmic scale, a continuous, humbling expansion of the frontier between what we know and what we have yet to discover. This journey into the unknown requires a certain mindset, one of awe and humility. As the renowned astrophysicist Neil deGrasse Tyson so aptly put it, the universe is under no obligation to make sense to you. That statement isn't a dismissal of our efforts to understand. It's a powerful reminder that we are the visitors here, trying to learn the rules of a realm that was not designed for our convenience. When we encounter something like dark energy, a force causing the entire universe to expand at an accelerating rate against all expectations, or detect a fast radio burst, a blistering flash of energy from a billion light years away that lasts mere milliseconds, we are being shown that our current toolbox of physics is incomplete. These phenomena challenge researchers not because scientists are missing something obvious, but because the solutions likely lie in entirely new branches of science, waiting to be written. The pursuit of these answers does far more than just satisfy our curiosity. unraveling a cosmic mystery has an incredible way of revolutionizing our daily lives and shifting our philosophical perspective. Consider how the quest to understand the motions of celestial bodies gave us Newton's laws of motion and universal gravitation, which in turn made everything from spaceflight to modern construction possible. Or how the strange principles of quantum mechanics, once a baffling theoretical playground, now form the absolute bedrock of the technology in the computer or phone you're using right now. Solving a mystery like dark matter isn't just about figuring out what's holding galaxies together. It could open doors to new forms of energy, new materials, or new understandings of the very fabric of spacetime. On a deeper level, each discovery redefines our place in the cosmos, challenging our anthropocentric views and reminding us that we are part of a much larger, grander, and more mysterious story. By taking a moment to appreciate the sheer depth and potential of these enigmas, we properly set the foundation for the incredible journey ahead, priming ourselves for the first mysterious realm we are about to step into. Now, let's take that metaphor of the cosmic city a little further. If everything we can see with our telescopes, every brilliant star, every swirling galaxy, every distant quasar, is just the glittering skyline, then dark matter is the massive, unseen foundation and the hidden framework upon which that entire city is built. We know it's there not because we can see it, but because we can see everything else moving as if it's there. It's the ultimate cosmic ghost, a substance that doesn't emit, absorb, or reflect a single particle of light, making it completely invisible to every form of electromagnetic observation we have. Yet its gravitational pull is unmistakable and overwhelming. Think about a galaxy spinning. The stars on the outer edges should be moving much slower than those near the center, just like planets in our solar system. But that's not what we observe. Those outer stars are whipping around at speeds that should send them flying off into the void. The only explanation is that they are being held in place by the immense gravitational grip of something we cannot see, a vast, massive halo of dark matter enveloping the galaxy. This isn't just a small miscalculation, it's a fundamental feature of the universe. Scientists now estimate that this mysterious substance makes up about 27% of all the mass and energy in the cosmos. That's over 5 times more abundant than all the ordinary matter, every atom that makes up you, me, our planet, and every star we can see combined. So what could it possibly be? The hunt for its identity is one of the greatest detective stories in all of science. The leading candidate for decades has been something called weakly interacting massive particles, or WIMP. These are theoretical particles that don't interact through the electromagnetic force but have mass, so they would exert gravity. To find them, physicists have built incredibly sensitive detectors deep underground in old mines and tunnels, places shielded from the cosmic rays and background radiation that would overwhelm their instruments. They wait, hoping to see the infinitesimal vibration, the faintest bump, that would signal a WIMP weakly colliding with an atom in their detector. But WIMP aren't the only suspect. Another intriguing idea is that dark matter could be made of primordial black holes. These wouldn't be the black holes formed from dying stars, but ones created in the incredibly dense, frenetic conditions of the Big Bang itself. They could be everywhere, and their gravity would perfectly explain the effects we see. Or perhaps our understanding of gravity itself is incomplete on the largest scales, and what we're seeing is not invisible matter, but a need to rewrite the laws first penned by Newton and refined by Einstein. The truth is, we still don't know, but every experiment, whether it's deep underground or in space with telescopes like Hubble and the new James Webb, brings us closer to an answer. Identifying this shadowy architect of the cosmos wouldn't just solve a puzzle, It would revolutionize physics, unlock secrets about the birth and ultimate fate of the universe, and perhaps reveal entirely new layers of reality hidden in plain sight all around us. Just when we thought we had a handle on the universe's expansion, thinking it must be gradually slowing down after the Big Bang's initial push, a discovery in the late 1990s sent a shockwave through cosmology. Two independent teams of astronomers were studying distant supernova, using these exploding stars as cosmic mile markers to measure how the expansion rate has changed over billions of years. They expected to see the expansion slowing, pulled by the collective gravity of all the matter in the cosmos. Instead, they found the exact opposite. The most distant supernova were fainter than predicted, meaning they were farther away than they should have been. The stunning, inescapable conclusion was that the universe's expansion isn't slowing down at all, it's speeding up. Something was overpowering gravity, pushing galaxies apart at an ever-increasing rate. That something was given a name that reflects our profound ignorance: dark energy. This revelation was so monumental it earned the researchers the Nobel Prize in Physics in 2011, and it completely upended our standard model of the cosmos. We now understand that dark energy isn't just a small effect. It is the dominant component of the universe, making up a staggering 68% of everything. Think about that for a moment. All the planets, stars, galaxies, and even the invisible dark matter we just discussed together constitute less than a third of the universe. The majority is this mysterious, repulsive force inherent to the fabric of empty space itself. The leading explanation for dark energy comes straight from Einstein's equations, though he initially considered it his greatest blunder. He introduced a term called the cosmological constant, representing a fixed energy density that fills the vacuum of space. If this constant has a positive value, it produces a repulsive gravitational effect, perfectly describing the acceleration we observe. In this view, dark energy is a permanent, unchanging property of the universe. But what if it's not constant? Another compelling theory suggests dark energy could be a dynamic field, nicknamed quintessence, that evolves and changes over time. This would mean the strength of this repulsive force could vary, potentially altering the ultimate fate of everything. This is the central question projects like the Dark Energy Survey and space telescopes like Euclid are desperately trying to answer. By meticulously mapping the positions and distances of millions of galaxies and measuring the distribution of cosmic structures, they are constructing a detailed history of the expansion, seeking tiny clues that could distinguish between a steady cosmological constant and a shifting quintessence field. The answer holds the key to our cosmic destiny. A true cosmological constant points toward a big freeze, where the universe expands forever, galaxies recede beyond sight, and the cosmos becomes a cold, dark, and empty void. A dynamic dark energy could lead to more dramatic fates, like a big rip, where the expansion eventually tears apart galaxies, solar systems, and even space-time itself. This enigmatic energy, hidden in the void, is the greatest puzzle in physics, a force that defines our future and challenges our grasp of reality at the most fundamental level. Now let's step right up to the very edge of one of the most fearsome and fascinating objects in the universe, a black hole. This is a place where the laws of physics as we know them are not just bent, but utterly broken. A region of space-time where gravity has become so overwhelmingly powerful that nothing, not even a single particle of light, can escape its pull once it crosses a point of no return known as the event horizon. It's the ultimate cosmic prison, a gravitational abyss from which there is no escape. But black holes are far more than just cosmic vacuum cleaners. They are natural laboratories, gateways to understanding some of the most profound mysteries of existence itself. We now know that black holes come in different varieties, each with its own dramatic origin story. The most common are stellar mass black holes, the grim tombstones of massive stars. When a star many times larger than our Sun exhausts its nuclear fuel, the outward pressure from fusion can no longer hold back the immense force of its own gravity. The star's core collapses catastrophically in a matter of seconds, triggering a supernova explosion that blasts the star's outer layers into space while the core continues to collapse inward, crushing down into an infinitely dense point, a singularity wrapped in an event horizon. Then there are the true monsters of the cosmos, supermassive black holes. These behemoths, weighing millions or even billions of times the mass of our Sun, reside at the very hearts of galaxies, including our own Milky Way. How they grew so immense so quickly in the early universe remains an open and active area of research, with some likely forming from the direct collapse of immense gas clouds or from the relentless merging of smaller black holes over cosmic time. For decades, black holes were purely theoretical, mathematical predictions of Einstein's theory of general relativity. That all changed in April 2019, when the Event Horizon Telescope collaboration released the first ever direct image of a black hole. This was not a photograph in the traditional sense, but a stunning radio image of the superheated gas swirling around the event horizon of the supermassive black hole at the center of the galaxy Messier 87. The image showed a brilliant, lopsided ring of light, the photon sphere encircling a dark shadow, which is the black hole's event horizon itself. This historic achievement provided the most direct visual confirmation that these incredible objects are real, and it opened a new window for testing gravity in its most extreme regime. Yet, for every question answered, a dozen new, deeper mysteries emerge. The greatest paradox of all lies at the very center of a black hole, the singularity. This is a point where density and gravity become infinite, and our current laws of physics simply cease to function. This tells us that a new theory, one that successfully merges Einstein's general relativity with the quantum mechanics of the very small, is needed to understand what truly happens there. This quest for a theory of quantum gravity is one of the holy grails of modern physics. Furthermore, the idea that information, the fundamental identity of every particle that falls in, could be lost forever in a black hole violates a key principle of quantum mechanics, leading to the famous black hole information paradox. This has prompted radical ideas like the holographic principle, which suggests that all the information about what falls into a black hole might not be lost, but instead encoded on its two-dimensional event horizon, like a cosmic piece of holographic film. This blending of hard science with concepts that sound like they're straight out of science fiction doesn't stop there. The extreme warping of space-time near a singularity has led to serious scientific speculation that black holes could be bridges to other places or times, wormholes, or even portals to other universes within a vast multiverse. While these ideas remain highly speculative and without any observational evidence, they push the boundaries of our imagination and demonstrate how black holes force us to confront the very nature of reality, time, and our place in the cosmos. They are the ultimate gateways to the unknown, challenging everything we think we know. If you thought black holes were enigmatic, try wrapping your mind around a cosmic signal that arrives without warning, delivers an unimaginable punch of energy, and then vanishes without a trace, all in less time than it takes to blink. These are fast radio bursts, or FRB, and they represent one of the most fleeting and powerful mysteries in the modern cosmos. Picture this: a single milliseconds-long burst of radio waves that, in that brief instant, can release more energy than our Sun puts out over the course of several days, sometimes even decades. It's an almost incomprehensible amount of power, focused into a flash of light that has traveled across billions of light-years of space to reach us, carrying with it the secrets of its origin and the material it passed through along the way. The story of their discovery is a perfect example of scientific serendipity. Back in 2007, a team of astronomers led by Duncan Lorimer was sifting through old archival data from the Parkes radio telescope in Australia, searching for new pulsars. Buried in that data was a signal so strong and so brief that it had been initially dismissed as terrestrial interference, perhaps a glitch from a nearby microwave oven. But this was different. It was a single, spectacular spike of radio energy that had all the hallmarks of coming from far outside our galaxy. They had accidentally uncovered the first evidence of a phenomenon that would launch an entirely new field of astrophysics. Since that first discovery, which became known as the Lorimer burst, hundreds of these events have been detected by radio telescopes around the world, painting a picture of a universe that is crackling with these incredibly powerful, incredibly brief cosmic whispers. What makes FRBs so fascinating to scientists isn't just their raw power, but their bewildering variety. Some of them are one-off events, a single, magnificent shout in the dark that is never heard from again. Others are repeaters, firing off multiple bursts from the same location in the sky, sometimes in predictable patterns and sometimes with chaotic randomness. This distinction is crucial because it strongly suggests there isn't just one single cause for all FRBs. Multiple cosmic catastrophes could be capable of producing these brilliant flashes. The fact that we've managed to trace many of them back to their host galaxies, often distant, modest galaxies billions of light-years away, rules out most local sources and confirms they are truly extragalactic events, making their immense energy output all the more astounding. So what cosmic engine could possibly be responsible for such brief, violent outbursts? The list of suspects is as exciting as it is varied. The leading natural candidate is a type of neutron star called a magnetar. We discussed these stellar remnants earlier, incredibly dense, city-sized objects with magnetic fields so powerful they could strip the information from your credit card from halfway across the solar system. The theory goes that a magnetar could experience a starquake, a sudden cracking of its rigid crust, which would release a titanic flare of energy that we would see as an FRB. Supporting this idea, in 2020, astronomers witnessed a magnetar within our own galaxy unleash a burst of radio energy that, while not quite as powerful as the extragalactic FRBs, was strikingly similar in nature. It was a smoking gun, suggesting that at least some FRBs indeed come from these magnetic monsters. Of course, the sheer power and mystery of these signals have also ignited more speculative ideas, including the possibility that they could be signatures of advanced extraterrestrial technology. Could an FRB be the equivalent of a cosmic lighthouse beam from an interstellar spacecraft, or perhaps an accidental byproduct of a massive energy project undertaken by a civilization far more advanced than our own? While most astronomers consider this an extremely remote possibility, the universe is usually stranger than fiction, and natural explanations almost always win out. It's a tantalizing thought that underscores just how little we truly understand about these signals. The real scientific value of FRBs, however, may not lie solely in identifying their source, but in what they can tell us about the vast, empty spaces between galaxies. As an FRB signal travels across the universe, it passes through clouds of ionized gas and the diffused plasma of the intergalactic medium. This material subtly slows down and disperses the different frequencies of the radio wave, an effect that scientists can measure. By analyzing this dispersion, astronomers can essentially use each FRB as a cosmic probe, allowing them to weigh the invisible ordinary matter that is scattered between galaxies, matter that has been notoriously difficult to account for. In this way, these mysterious bursts are becoming vital tools for mapping the cosmic web itself. This incredible effort to catch and understand these fleeting whispers is being led by a new generation of powerful radio telescopes, most notably the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. Unlike a traditional steerable dish, CHIME is a stationary array of over 1,000 antennas that stares fixedly at the sky as the Earth rotates, allowing it to sweep a huge portion of the heavens every single day. This makes it the perfect instrument for catching random, transient events like FRBs, and it has revolutionized the field by detecting thousands of them, providing the vast statistical sample needed to finally start classifying them and narrowing down their origins. Each new detection is another piece of the puzzle, another whisper from the cosmos that brings us closer to understanding one of its most energetic and elusive phenomena. If you thought the fleeting power of a fast radio burst was intense, prepare yourself for the true titans of cosmic violence, gamma-ray bursts. These are not mere whispers or flashes. They are the universe's ultimate tantrums, the most powerful and luminous explosions known to occur since the Big Bang itself. To even begin to grasp their scale, consider this. In a span of just a few seconds, a single gamma-ray burst can unleash more energy than our Sun will emit over its entire 10 billion-year lifespan. It is a concentration of power so absolute, so unfathomably dense, that it defies all earthly comparison. These events are the birth cries of newborn black holes and the death throes of massive stars, cosmic beacons that briefly outshine every other source of gamma rays in the entire sky. Their discovery is a classic tale of scientific serendipity born from the tension of the Cold War. In the 1960s, the United States launched the Vela satellite series, not to peer into the depths of space, but to monitor the Earth for secret nuclear weapons tests which were banned by treaty. These satellites were designed to detect the telltale signature of gamma radiation that a nuclear detonation would produce. To the surprise of the scientists analyzing the data, they began picking up intense bursts of gamma rays, but these weren't coming from anywhere on Earth. They were originating from deep space, appearing randomly from all directions across the sky. For years, this data was kept secret within the military. But once it was declassified and shared with the astronomical community, it sparked a decades-long quest to understand the origin of these mysterious, universe-shaking events. We now know that gamma-ray bursts are not all the same. They come in two distinct varieties, each with its own terrifyingly dramatic origin story. The first type are the long-duration bursts, which last anywhere from 2 seconds to several minutes. These are thought to be associated with the deaths of the most massive stars in the universe, events known as hypernova. When a star dozens of times more massive than our Sun finally exhausts its nuclear fuel, its core collapses not just into a neutron star, but directly into a black hole. As it does so, powerful jets of material are launched from its poles at nearly the speed of light. If one of those incredibly focused jets happens to be pointed directly at Earth, we see it as a long gamma-ray burst, a blindingly bright flash signaling the creation of a new black hole at the heart of a spectacular stellar explosion. The second type are the short-duration bursts, which are even briefer, lasting less than 2 seconds and often just a few milliseconds. These are believed to be the result of a different but equally cataclysmic cosmic event, the merger of two ultra-dense stellar remnants. Picture two neutron stars or a neutron star and a black hole, locked in a final, fatal gravitational dance. After spiraling inward for millions of years, they finally collide and coalesce, creating a new black hole in a violent splash of energy and ripples in spacetime. Just like with the long bursts, this event also launches relativistic jets, and if we are in the path of one, we witness a short, incredibly intense gamma-ray burst. The historic detection of gravitational waves from a neutron star merger in 2017, which was accompanied by a short gamma-ray burst and a brilliant kilonova that forged heavy elements like gold and platinum, provided stunning confirmation for this theory, marking a new era of multi-messenger astronomy. Catching these brief, unpredictable events requires a fleet of vigilant sentinels in space. Satellites like NASA and Neil Gehrels Swift Observatory and the Fermi Gamma Ray Space Telescope constantly scan the skies for these flashes. The moment one is detected, these satellites automatically and rapidly swing into action, slewing to point their other instruments at the location to capture the fading afterglow, the lingering emission at X-ray, ultraviolet, and optical wavelengths that can last for hours or days. This afterglow is crucial. It allows ground-based telescopes to pinpoint the burst's exact host galaxy, often revealing it to be billions of light-years away, and providing a wealth of data about the event itself and the distant galaxy it calls home. This incredible power, capable of being seen across such vast cosmic distances, makes gamma-ray bursts incredibly useful tools. Astronomers use them as cosmic lighthouses. The light from a burst, as it journeys to Earth, passes through the gas and dust of its own host galaxy and the intergalactic medium, imprinting a spectral fingerprint on the afterglow. By analyzing this fingerprint, scientists can determine the composition of matter in these incredibly distant galaxies, effectively using these explosions to probe the conditions of the early universe. But this same power also poses a profound existential question. A gamma-ray burst occurring within our own galaxy and aimed directly at us would be a civilization-ending event. The intense radiation would likely strip away Earth's protective ozone layer, exposing the planet to deadly levels of ultraviolet radiation from the sun and potentially triggering a mass extinction. Some scientists even speculate that one such event may have been responsible for the Ordovician extinction millions of years ago. This frightening possibility reminds us that the universe, for all its beauty, is also a place of immense and unpredictable violence, where the fate of life on a planet can be decided by a stellar catastrophe occurring light-years away. But the drama of a supernova's final act doesn't just leave behind an empty stage. It forges one of the most extreme and fascinating objects in the entire universe, a neutron star. Picture the core of a massive star, a region that was once the powerhouse of nuclear fusion, suddenly finding itself without the outward pressure to fight the immense crush of its own gravity. In less than a single second, this core, which is already more massive than our entire sun, collapses down from a sphere hundreds of miles wide to a city-sized ball barely 12 miles across. The force of this collapse is so unimaginably violent that it forces protons and electrons to merge, cancelling their charges and transforming almost the entire mass into a solid ball of neutrons. The result is an object with a density so staggering it defies all earthly logic. A single sugar cube-sized piece of this material would not weigh a few grams. It would weigh over 1 billion tons, a mass equivalent to a mountain range crushed into a speck you could hold between your fingers. This isn't just a dense object, it's a natural laboratory for physics under conditions we could never hope to recreate on Earth. The surface gravity is so intense that if you were to somehow drop a marshmallow onto it from just a meter away, it would impact with the force of 1,000 hydrogen bombs. And if its density isn't enough to boggle the mind, consider its magnetic power. Some neutron stars, known as Magnetars, possess magnetic fields that are 1,000 trillion times stronger than Earth's. A magnetar located halfway between the Earth and the Moon would effortlessly strip the magnetic data from every credit card on the planet. These fields are so powerful they can actually twist the star's rigid crust, causing starquakes that release colossal flares of X-rays and gamma rays, briefly making the magnetar the brightest object in the entire gamma-ray sky. Yet for all their mind-bending properties, some neutron stars reveal themselves to us in an even more spectacular way, as pulsars. If a neutron star is spinning rapidly, and many are born rotating hundreds of times per second, and if its powerful magnetic field is misaligned with its rotation axis, it acts like the most powerful cosmic lighthouse ever conceived. Beams of radiation focused by the magnetic fields shoot out from its magnetic poles. As the star spins, these beams sweep across the cosmos. If one of those beams happens to sweep across our line of sight here on Earth, we detect a perfectly timed pulse of radio waves, or sometimes X-rays or gamma rays, with a regularity that rivals the most precise atomic clocks. The discovery of pulsars in the 1960s was initially so periodic that astronomers half-jokingly nicknamed the first source LGM for Little Green Men, before the true natural explanation was understood. Today, we use these cosmic lighthouses for incredible feats of science, like testing Einstein's theory of general relativity, and even for attempted navigation for future interstellar spacecraft. Perhaps the most significant role neutron stars play, however, is as cosmic forges for the universe's most precious heavy elements. For a long time, scientists knew that elements like carbon and oxygen were cooked in the hearts of stars, and that the very heaviest elements like iron were forged in the final moments of a supernova explosion. But there was a problem. The supernova model alone couldn't account for the sheer abundance of elements like gold, platinum, and uranium in the universe. The answer came in 2017 with a landmark event. For the first time, astronomers detected both gravitational waves and light from the same source, the cataclysmic collision of two neutron stars. The event, known as GW170817, was a scientific bonanza. The ripples in spacetime told us about the masses of the objects, while the brilliant afterglow, called a kilonova, revealed the spectroscopic signature of newly created heavy elements being blasted into space. In that one violent merger, it's estimated that an amount of gold equivalent to several times the mass of our Earth was synthesized and scattered across the galaxy. This means that the gold in your wedding ring or the platinum in a catalytic converter was almost certainly born in the incredible violence of two dead stars smashing together billions of years ago. This ability to study neutron star mergers through both gravitational waves and light. A field known as multi-messenger astronomy has given us an unprecedented window into their mysterious interiors. The extreme pressure at the core of a neutron star might be squeezing matter into forms we can only theorize about. A superfluid soup of free-floating quarks, a bizarre state nicknamed nuclear poster, or other exotic phases that blur the line between matter and energy. By observing the gravitational wave signals from these collisions, scientists can infer how stiff or soft the neutron star matter is, which in turn tells us about the fundamental strong nuclear force that holds atomic nuclei together. Each merger is like a cosmic bell being struck. The ring of gravitational waves it produces carries the signature of the star's internal composition, allowing us to probe matter in a state that will forever be beyond the reach of any Earth-bound laboratory. Now, let's turn our attention to one of the most purely theoretical and mind-bending concepts in all of cosmology, the white hole. If a black hole is a cosmic one-way street where everything can fall in but nothing can ever get out, then a white hole is its exact theoretical opposite, a region of spacetime where nothing can ever enter, but matter and energy can only pour outward. It's as if a black hole were playing in reverse, a cosmic fountain endlessly spewing material into the universe rather than a drain sucking it all down. This isn't just a fanciful idea. It emerges directly from the same complex mathematics of Einstein's theory of general relativity that predicted black holes in the first place. In fact, the equations are perfectly symmetric with respect to time, meaning that if a black hole is a valid solution, then its time-reversed counterpart, a white hole, should also, in theory, be possible. The challenge, of course, is that while we have overwhelming observational evidence for the existence of black holes, we have precisely zero for white holes. No telescope has ever detected a point in space that is violently and continuously expelling matter without any apparent source. This has led many physicists to relegate white holes to the realm of mathematical curiosities, interesting solutions to the equations that simply don't manifest in our physical reality, perhaps because they violate the second law of thermodynamics. Entropy, the measure of disorder in a universe, always increases, and a white hole, which seems to create order by spewing out structured energy, appears to fly in the face of this fundamental principle. So why do serious scientists continue to entertain the idea? Because in the quest for a deeper theory of quantum gravity, white holes have made a surprising and compelling comeback. Some of the most cutting-edge approaches to unifying general relativity with quantum mechanics, particularly a theory called loop quantum gravity, have provided a fascinating new potential life raft for the white hole concept. This theory suggests that the immense gravitational collapse that forms a black hole might not actually culminate in an infinitely dense singularity, a point where physics breaks down. Instead, at a certain extreme threshold, quantum gravitational effects would become so powerful that they would generate a repulsive force, causing the collapsing material to rebound in a massive, explosive reversal. In this scenario, what we perceive as a black hole from the outside would, after an almost unimaginably long period of time, transform into its opposite, a white hole, effectively recycling the information and energy it had once consumed back out into the universe. This would solve the infamous black hole information paradox and provide a mechanism for the universe to avoid the destructive finality of singularities. The implications of this are staggering. If white holes are real, they would completely upend our understanding of causality, the relationship between cause and effect. They could act as bridges or portals, potentially connecting different parts of our universe, or even acting as gateways to entirely separate universes within a vast multiverse. A journey into a black hole might not end in oblivion, but could instead be a tunnel through to another reality, exiting from a white hole on the other side. While this sounds like the plot of a science fiction movie, it's a legitimate, albeit highly speculative, area of theoretical research. It forces us to confront profound questions about the very nature of time, the conservation of information, and whether the universe might possess a mechanism for cosmic recycling on the grandest of scales. Though they remain a spectacular what-if, white holes are a perfect example of how theoretical physics uses extreme ideas to test the boundaries of our knowledge, pushing us to think about what might be possible in the strange and wonderful fabric of spacetime. While black holes represent a terrifying point of no return and white holes remain a speculative exit, the concept of a wormhole offers perhaps the most tantalizing possibility of all, a cosmic shortcut. Imagine the universe not as a vast, empty expanse that would take tens of thousands of years to cross, but as a folded piece of paper. A wormhole would be like a pencil poking through that fold, creating a tunnel, a bridge, that instantly connects two points that would otherwise be impossibly far apart. This isn't just a fanciful idea from science fiction. It's a legitimate, though entirely hypothetical, solution that emerges from the same equations of Albert Einstein's theory of general relativity that describe black holes and the curvature of space-time itself. The story of their theoretical discovery is a fascinating chapter in the history of physics. In 1935, Albert Einstein and his colleague Nathan Rosen were working through the complex mathematics of general relativity, specifically exploring the implications of what we now call a Schwarzschild black hole, a simple, non-rotating model. They realized that the equations allowed for a peculiar structure, a bridge connecting two separate points in spacetime. This structure, which they called an Einstein-Rosen bridge, was initially thought to be nothing more than a mathematical curiosity, a quirky feature of the equations that couldn't possibly exist in the real world because it would be incredibly unstable and would collapse instantly upon formation. It was science fiction authors, most notably John Wheeler, who later coined the term wormhole in the 1950s, who truly popularized the idea and sparked the public's imagination about their potential as portals for interstellar travel. The fundamental problem with any wormhole, however, is stability. According to general relativity, the immense gravitational forces at play would cause the throat of the tunnel to pinch off faster than even a single photon of light could travel through it. To prevent this instantaneous collapse, you would need a very special kind of material to line the walls of the wormhole and act as a counterbalancing force. This isn't just any ordinary matter. Physicists refer to it as exotic matter. This hypothetical substance would need to possess a negative energy density, effectively creating a form of anti-gravity that repels rather than attracts, propping the tunnel open and making it traversable. While we have observed tiny, microscopic effects that hint at the possibility of negative energy, such as in the Casimir effect between two very close metal plates, the amounts needed to stabilize a wormhole large enough for a spaceship are far beyond anything we can currently conceive of creating. This requirement for exotic matter is what firmly plants wormholes in the realm of theory for now, but it hasn't stopped physicists from exploring their incredible potential. If a stable, traversable wormhole could exist, the implications would be nothing short of revolutionary. The most obvious application is for interstellar travel. A journey to a star system tens of thousands of light years away could, in theory, be reduced to a trip that takes mere days or hours through the right wormhole network, turning humanity into a truly interstellar species almost overnight. But the possibilities get even stranger when you consider the nature of spacetime itself. According to Einstein's theories, space and time are interwoven. A wormhole that connects 2 points in space could also potentially connect 2 points in time. This is where the concept of a wormhole becomes a theoretical time machine. Imagine one end of a wormhole is placed on a super-fast spaceship accelerating to near the speed of light. Due to the effects of time dilation from special relativity, time would pass more slowly for the end of the wormhole on the ship compared to the end that remained stationary on Earth. If the ship then returned, the two ends would be out of sync. Entering one end might allow you to exit the other end not just in a different location, but in a different time, either in the past or the future. This doesn't automatically create the paradoxes of going back and preventing your own birth, as the rules of such time travel are tightly constrained by physics, but it opens a dizzying array of questions about causality and the fundamental flow of time in our universe. The ongoing scientific research into wormholes, while purely theoretical, is far from idle speculation. By rigorously studying these hypothetical objects, physicists are stress-testing the limits of general relativity and exploring how it might be reconciled with quantum mechanics. The quest to understand what kind of physics could allow for exotic matter and stable wormholes is deepening our knowledge of quantum field theory, vacuum energy, and the very nature of the fabric of spacetime. Each paper published is a step toward a more complete theory of quantum gravity. Even if the wormholes themselves remain elusive, they serve as a powerful thought experiment, a tool for asking the biggest questions about what is physically possible in our cosmos, and in doing so, they bridge our understanding toward other profound mysteries that challenge our perception of reality itself. Now, let's shift our gaze from the theoretical fabric of spacetime to a very real and powerful force acting upon our own galactic neighborhood, a mysterious, unseen presence that is actively pulling our entire Milky Way galaxy, along with countless others, through the cosmos at a breathtaking speed of over 1 million miles per hour. This is the enigma of the Great Attractor, a colossal gravitational anomaly that serves as a stark reminder of how much of the universe remains hidden from our view, dictating the motions of galaxies from the shadows. For decades, astronomers have been aware that our local group of galaxies is not moving randomly. It is part of a vast, coherent flow, a cosmic river of stars and dark matter all being drawn toward a specific point in the sky, deep within the constellation of Centaurus. This relentless pull suggests the presence of an immense concentration of mass, a gravitational anchor so powerful it can influence the motion of thousands of galaxies across hundreds of millions of light-years. The story of its discovery begins in the 1970s and 80s, when astronomers were first mapping the large-scale velocities of galaxies. By measuring the redshift of their light, how much it stretched by the expansion of the universe, they could calculate how fast each galaxy should be moving away from us. But they noticed something peculiar. Galaxies in a huge swath of the sky, including our own, were all deviating from this expected Hubble flow. Their actual velocities had an extra component, a shared drift toward this one specific region. It was as if every single one was caught in the same invisible current, being pulled toward a destination we couldn't see. This was the first compelling evidence for a gravitational overdensity of staggering proportions, a cosmic magnet that earned the name the Great Attractor. But why has identifying this attractor been so incredibly difficult? The answer lies in its location from our perspective here on Earth. It resides in a direction that is almost perfectly aligned with the plane of our own Milky Way galaxy. This region is known to astronomers as the zone of avoidance. It's not that there's nothing there, it's that our view is completely obscured by the thick bands of gas, dust, and countless stars that make up the galactic disk of our own spiral galaxy. It's like trying to see a distant mountain range through a dense, persistent fog bank. For the longest time, this zone was a blind spot in our maps of the universe, a blank area on the celestial charts where optical telescopes could simply not peer through the murk. This is where the ingenuity of modern astronomy comes into play. To see the unseen, we must look in wavelengths of light that can penetrate the cosmic dust. Radio waves and infrared light can pass through this obscuring material where visible light cannot. Pioneering surveys using these tools, most notably the 2-micron all-sky survey, or 2MASS, which mapped the sky in infrared light, began to peel back the veil. What they revealed was that the Great Attractor isn't necessarily a single, monstrous object. The pull we feel is likely the combined gravitational influence of an enormous conglomerate of mass, most probably a massive cluster of galaxies or even a supercluster, and not in the cosmic web where many galaxy clusters are drawn together by their mutual gravity. In fact, we now know that our own local group and the Virgo cluster are all part of a much larger structure called the Laniakea supercluster, and the Great Attractor seems to form the central gravitational core of this vast cosmic continent, a focal point toward which everything in our local neighborhood is slowly, inevitably flowing. The true nature and full extent of the Great Attractor remain active topics of research. Is it one incredibly dense cluster, or is the pull we feel actually the result of an even larger structure beyond it, like the mind-bogglingly immense Shapley supercluster, which lies further away in the same general direction and may itself be tugging on the Great Attractor? This highlights a fascinating aspect of cosmology. The universe has structure on scales we are still struggling to comprehend, with gravitational influences cascading from one supercluster to the next. To finally solve this puzzle, we need even more powerful tools capable of mapping the cosmos in extraordinary detail through the zone of avoidance. This is the mission of next-generation projects like the Square Kilometre Array, or SCAR, a revolutionary radio telescope network that will peer through the galactic plane with unprecedented clarity, charting the distribution of hydrogen gas in millions of galaxies and ultimately creating a full three-dimensional map of the gravitational forces at play. By unraveling the mystery of the Great Attractor, we don't just identify what's pulling us, we gain a profound understanding of the architecture of the universe on the grandest of scales, revealing the hidden skeleton of dark matter upon which the visible cosmos is built. After exploring the immense gravitational pull of the Great Attractor, we now journey into the profound emptiness that lies between these cosmic hubs of matter. We are venturing into the cosmic voids, the universe's true deserts. These are not small, empty pockets but colossal regions of space, some stretching over 300 million light-years across, that are almost completely devoid of galaxies, stars, and even the familiar clouds of gas and dust. If the universe's large-scale structure is a vast cosmic web made of brilliant filaments and dense clusters of galaxies, then these voids are the enormous dark holes in that web. They represent the dominant volume of the universe, immense expanses of near-nothingness that challenge our very understanding of how the cosmos organized itself after the Big Bang. The existence of these voids is a direct challenge to classical models of structure formation. In the early universe, slight fluctuations in density were amplified by gravity over billions of years. Matter collapsed into the dense knots and filaments we see as galaxy clusters and superclusters, but this process also had a flip side. As matter flowed into these dense regions, it had to drain away from others. The voids are the result of this cosmic evacuation. They are not static empty bubbles, they are dynamic regions that have been expanding and becoming ever emptier over time. Their incredibly low density means the gravitational forces within them are weak, allowing the expansion of space itself to proceed faster inside a void than in the crowded galactic clusters. This makes them crucial natural laboratories for studying dark energy, the mysterious force accelerating the universe's expansion, as its effects are more pronounced in these underdense regions. Mapping these empty expanses is a monumental task that requires surveying the sky in unprecedented detail. Projects like the Sloan Digital Sky Survey have been instrumental in this effort. By meticulously measuring the redshifts and positions of millions of galaxies, these surveys allow astronomers to construct breathtaking three-dimensional maps of the universe. These maps don't just show us where the galaxies are, they reveal with stunning clarity the shape and scale of the vast empty spaces between them. We can see the void network as a complex foam-like structure, with galaxy filaments forming the walls of these enormous bubbles. The largest known void, the Boötes void, is so immense and empty that it was nicknamed the Great Nothing, containing only a handful of galaxies where thousands would be expected. Studying these voids is about more than just cataloging emptiness. It provides profound insights into the fundamental forces shaping our cosmos. The way these voids grow and evolve tells us about the strength of gravity and the nature of the dark energy working against it. The precise shapes and sizes of the voids are sensitive probes for cosmological parameters, helping scientists test different models of the universe's composition and fate. Furthermore, the eerie environment within a void is a unique astrophysical setting. The rare galaxies that do form inside these deserts are isolated, evolving in near-total solitude without the frequent galactic collisions and interactions that shape galaxies in clusters. This isolation makes them fascinating subjects for understanding galactic evolution in its most pristine form. The profound quietude of these cosmic deserts, where the night sky would be almost perfectly black, stands in stark contrast to the brilliant, chaotic energy of the phenomena we explore next. Gaze across the cosmos and you might spot what appears to be a brilliant, unassuming star. But this is no star, it is a deception of distance and power, one of the most luminous objects in the entire universe, a quasar. The name itself is a clue to its initial mystery, short for quasi-stellar radio source. In the 1950s, as radio astronomy began to flourish, these points of light appeared star-like through optical telescopes but emitted staggering amounts of radio energy, a combination that utterly baffled scientists. The puzzle only deepened when their spectra were analyzed, revealing immense redshifts that placed them not in our galaxy, but billions of light years away. For an object so distant to appear so bright, it had to be unleashing almost unimaginable power, outshining the combined light of every single star in a typical galaxy by a factor of 100 or even 1,000. The question was, what cosmic engine could possibly generate such staggering brilliance? The answer, we now know, lies in the ultimate cosmic paradox, the marriage of supreme light and absolute darkness. At the heart of every quasar sits a supermassive black hole, a gravitational monster weighing millions or even billions of times the mass of our Sun. But a black hole alone is an inert vacuum. It is the frenetic activity around it that creates the spectacle. As vast clouds of gas, dust, and even entire stars are drawn inward by the black hole's immense gravity, they don't simply fall straight in. Instead, they form a swirling, flattened, superheated structure called an accretion disk, whirling around the event horizon, a T Chinese letter, the speed of light. The friction and tidal forces within this disk heat the material to temperatures of millions of degrees, causing it to glow with intense radiation across the entire electromagnetic spectrum, from X-rays to radio waves. This process of accretion, the black hole feeding, is so efficient at converting mass into energy that it dwarfs the output of nuclear fusion in stars. The terrifying darkness of the singularity is thus surrounded by the most radiant beacon imaginable, a lighthouse whose beam can be seen from the farthest reaches of the observable universe. This incredible luminosity makes quasars more than just spectacular cosmic fireworks. They are indispensable tools for cosmologists. Because they are so bright, they can be seen at truly enormous distances, acting as probes into the early history of the universe. The light from the most distant quasars has been traveling for over 13 billion years, meaning we are seeing them as they were when the universe was less than 1 billion years old. By analyzing the spectrum of this ancient light, astronomers can piece together the conditions of the infant cosmos. For instance, as the quasar's light journeys to Earth, it passes through immense clouds of intergalactic hydrogen gas. This gas absorbs specific wavelengths of light, creating a forest of absorption lines in the quasar's spectrum. This Lyman alpha forest, as it's called, allows scientists to map the distribution and temperature of matter between galaxies, charting the cosmic web in its early stages of formation. Quasars are, in effect, brilliant backlights illuminating the universe's primordial skeleton. Beyond their role as cosmic lighthouses, quasars provide a front-row seat to the violent and dynamic processes governing the growth of galaxies. Many quasars don't just emit radiation, they also fire out colossal, narrow jets of plasma from their poles at velocities approaching the speed of light. These jets, extending for hundreds of thousands of light-years, are thought to be channeled and accelerated by the black hole's powerful magnetic fields. They are a clear sign that the black hole is not just consuming matter, but also ejecting a fraction of it back into space with tremendous force. This feedback process is now understood to be crucial to galaxy evolution. The intense radiation and powerful jets from a quasar can heat up or blow away the surrounding gas in its host galaxy. Since this gas is the raw material for forming new stars, a quasar can effectively shut down star formation in its galaxy, putting a limit on its growth. It's a fascinating cycle. The supermassive black hole feeds and grows, eventually becoming so powerful that it regulates the very environment that feeds it. A dramatic demonstration of how the largest structures in the universe are shaped by the smallest, most extreme points within them. With the deployment of the James Webb Space Telescope, our understanding of these ancient beacons is entering a revolutionary new phase. JWST's incredible infrared sensitivity is allowing astronomers to peer through the blinding glare of the quasar itself and directly observe its host galaxy for the first time at these extreme distances. We are now beginning to see the galactic homes that nurtured these monstrous black holes so soon after the Big Bang, understanding how they formed and grew to such immense sizes so quickly. This is helping to solve one of the biggest puzzles in modern astrophysics: how the supermassive black holes we see in the early universe could have possibly had enough time to grow to billions of solar masses. Each new observation peels back another layer of the quasar mystery, revealing not just the nature of these incredible objects, but also the intimate and powerful connection between a galaxy and the dark heart that beats at its center, governing its destiny across cosmic time. But if you thought a typical neutron star was a monument to cosmic extremes, prepare to meet its far more volatile and terrifyingly powerful cousin, the Magnetar. This is a neutron star that has dialed every single one of its already insane properties up to 11, most notably its magnetic field. To even begin to grasp the scale of this power, consider this common analogy. An ordinary refrigerator magnet has a field strength of about 100 Gauss. The Earth's own protective magnetic field measures a gentle 0.5 Gauss. A typical neutron star, a pulsar, can have a field of 1 trillion Gauss. But a magnetar, its magnetic field is 1,000 times stronger than that, reaching an almost incomprehensible 1,000 trillion Gauss. This is a level of magnetism so profound it literally warps the very nature of reality around it. At such intensities, the magnetic field is powerful enough to distort the electron clouds inside atoms, effectively stretching them into long, thin, needle-like rods. A magnetar located just halfway between the Earth and the Moon, a distance of about 120,000 miles, would not just disrupt compasses, it would effortlessly scramble the magnetic strip on every credit card on the planet and utterly wipe every form of magnetic storage media, from hard drives to phone chips, rendering our digital world instantly useless. It is a force of nature so absolute it defies any earthly comparison. This unimaginable magnetic power doesn't just sit there passively, it actively tortures the star itself. The magnetar's crust is a rigid, incredibly dense lattice of iron nuclei. The titanic magnetic fields exert immense stress on this crust, bending and twisting it over time. Eventually, just like tectonic plates on Earth, the crust can't take the strain anymore. It cracks, but this isn't a mere earthquake, it's a starquake. The energy released in this sudden, catastrophic event is apocalyptic. In a fraction of a second, the magnetar can unleash a flare of X-rays and gamma rays that, for a brief moment, makes it the brightest object in the entire gamma-ray sky, outshining every other source in the universe combined, including the Sun. The most famous such event occurred in 2004, when a magnetar named SGR 1820-20, located 50,000 light-years away in the constellation Sagittarius, unleashed a starquake. The radiation that hit our upper atmosphere was so powerful that it actually ionized atoms, briefly expanding the Earth's ionosphere and disrupting long-range radio communications. To have a measurable effect on our planet from clear across the galaxy is a staggering demonstration of raw cosmic power. Like all neutron stars, magnetars are the collapsed cores of once massive stars, born in the fiery crucible of a supernova explosion. However, astronomers believe that for a neutron star to become a magnetar instead of a regular pulsar, the progenitor star likely needed to be spinning exceptionally fast and have an unusually powerful magnetic field even before it died. During the collapse, the core's spin and magnetic field are amplified dramatically, a process akin to an ice skater pulling their arms in to spin faster, but on a cosmic scale with almost unimaginable forces. This creates the perfect engine for magnetic amplification, resulting in the birth of this stellar monster. They are also relatively rare and short-lived in cosmic terms. Their immense magnetic fields are thought to decay after about 10,000 years, a mere blink of an eye in astronomy, after which they become far quieter, more typical neutron stars. This ephemeral nature makes catching one in its active, flaring phase a rare and precious event for astronomers. Studying these magnetic leviathans is about far more than just cataloging cosmic violence. They provide a unique natural laboratory for probing the behavior of matter and energy under conditions that we could never hope to recreate in any laboratory on Earth. The physics of how such intense magnetic fields are generated and sustained touches upon fundamental questions in quantum electrodynamics and particle physics. By observing the X-ray pulses and outbursts from magnetars using space-based observatories like NASA Chandra X-ray Observatory and the Neil Gehrels Swift Observatory, scientists can indirectly map the structure of these magnetic fields and understand how they interact with the super-dense matter of the star's interior and crust. Each flare is a data point, a message from the extreme edge of physics that helps us understand the limits of magnetic field strength in the universe and the ultimate fate of matter crushed into such incredible densities. Their volatile and explosive nature firmly connects them to the family of transient high-energy events we've been exploring, serving as a likely explanation for some of the mysterious short-duration gamma-ray bursts and perhaps even certain types of fast radio bursts, reminding us that the cosmos is a dynamic and often violently unpredictable place. Now let's redefine what it means to be a planet. We're taught from a young age that planets are orderly worlds, dutifully orbiting a parent star in a predictable dance. But what if we told you that the galaxy is teeming with worlds that follow no such rules? These are rogue planets, the ultimate cosmic nomads, lonely, dark, and untethered to any star, drifting endlessly through the frigid emptiness of interstellar space. Picture a world like Jupiter or even Earth, but cast out from its solar system, destined to wander the void between the stars, where the only light comes from the distant, fading glow of the galaxy itself. It's a profoundly different, almost haunting vision of what a planet can be, and it challenges the very definitions astronomers have used for centuries. How do these solitary worlds come to exist? Their origins are as dramatic as their journeys. Some rogue planets are likely formed the same way stars are, from the collapse of a small, dense cloud of gas and dust. In these failed star scenarios, the cloud wasn't quite massive enough to ignite fusion in its core, leaving behind a Jupiter-like object that never had a sun to begin with. But many more are thought to be the tragic results of cosmic violence planets that were born into a regular solar system, only to be violently ejected by the gravitational slingshot of a passing star or the unstable interactions with their sibling planets during the system's chaotic early years. It's a staggering thought that our own solar system, in its youth, may have flung several of its original planets out into the cold darkness, a reminder that cosmic evolution can be a brutal and unforgiving process. The sheer scale of this nomadic population is almost beyond comprehension. While we have confirmed the existence of only a few dozen so far, statistical models based on gravitational microlensing surveys suggest they are astonishingly common. Some estimates indicate there could be billions, perhaps even trillions, of these free-floating worlds adrift in our Milky Way galaxy alone, outnumbering stars by a significant margin. This means the dark, empty space between stars is not truly empty at all. It is a hidden archipelago of uncharted worlds, a vast and unseen population that has been largely invisible to us until very recently. Finding these dark, lonely wanderers is one of the greatest technical challenges in modern astronomy, since they emit no light of their own and are too far from any star to reflect significant light. Traditional telescope surveys simply can't see them. So how do we find them? Astronomers rely on two ingenious, indirect methods. The first is gravitational microlensing. This occurs when a rogue planet's gravity, as it drifts through space, acts as a tiny lens, briefly bending and magnifying the light from a far more distant star behind it. For a short period, this star appears to brighten in a very specific, telltale way, betraying the presence of the invisible planetary lens that passed in front of it. It's an incredibly difficult observation, like detecting a speck of dust by the shadow it casts from a mile away, but it has proven remarkably successful. The second method is direct imaging with the most advanced telescopes we have. While a rogue planet is dark, it is not completely cold. Especially the larger, younger ones retain significant heat from their formation, glowing faintly in the infrared part of the spectrum. Telescopes like the James Webb Space Telescope, with their incredibly sensitive infrared detectors, are now capable of spotting these faint embers against the black velvet of space. By taking extremely long exposure images and using sophisticated coronagraphs to block out the light of any nearby stars, astronomers can sometimes capture the direct, ghostly image of a rogue planet, a solitary pinprick of warmth in the eternal cold. The most captivating question surrounding these orphaned worlds is perhaps the most profound. Could they harbor life? At first glance, the idea seems ludicrous. A planet with no sun would be a frozen, airless wasteland, its surface temperatures hovering just a few degrees above absolute zero. But science often reveals possibilities stranger than fiction. Many larger rogue planets, particularly those with thick hydrogen atmospheres, could trap enough internal heat from radioactive decay and their primordial formation to maintain vast, global subsurface oceans of liquid water, sealed beneath a thick crust of ice. We see a similar phenomenon on moons like Europa and Enceladus in our own solar system, which are heated not by the sun but by the gravitational tug of war with their host planet. A rogue planet would be its own source of heat. In such a dark, subsurface ocean, shielded from the harsh radiation of space, life could potentially arise and persist, powered not by photosynthesis but by chemosynthesis, drawing energy from hydrothermal vents on the ocean floor, much like the exotic ecosystems found in the deepest, darkest trenches of Earth's oceans. The possibility that the most common habitable environments in the galaxy might not be Earth-like planets orbiting stars, but instead these isolated, sunless worlds drifting in the abyss, is a concept that completely upends our search for life elsewhere in the universe. This expansion of the habitable zone concept is a key goal for upcoming missions. The Nancy Grace Roman Space Telescope, set to launch later this decade, will conduct a wide-field microlensing survey that is expected to discover thousands of these rogue planets, finally giving us a reliable census of their population. By studying their numbers, masses, and trajectories, we will learn invaluable information about the formation and dynamics of planetary systems in general, revealing how common planetary ejections really are. Each discovery is a step toward understanding the full diversity of worlds in our galaxy, reminding us that a planet doesn't need a sun to be fascinating. It just needs to exist, a silent testament to the dynamic and often unpredictable nature of cosmic creation. After exploring the profound isolation of rogue planets, our attention is drawn to a fleeting visitor that proved we don't have to leave our own solar system to encounter something truly alien. In October 2017, astronomers at the University of Hawaii made an extraordinary discovery using the Pan-STARRS telescope. They spotted a faint, fast-moving object hurtling through our solar system. But its trajectory was unlike anything ever seen before. It was hyperbolic, meaning it was not bound by the sun's gravity. This was no asteroid or comet from our own cosmic backyard. Calculations confirmed it was the first known interstellar object ever detected, a visitor from the vast space between the stars. It was given the name ʻOumuamua, a Hawaiian word meaning a messenger from afar arriving first. From the very beginning, ʻOumuamua was shrouded in mystery. As telescopes around the world swiveled to observe it, they struggled to pin down its basic properties. The most immediate and startling puzzle was its shape. By measuring how its brightness changed dramatically over periods of hours, astronomers inferred that it was not a roundish object like most asteroids and comets. Instead, it was either highly elongated, like a cosmic cigar, or possibly very flat, like a pancake. This was an unusual form, suggesting it might have undergone a unique and violent formation process in its home star system, one that could stretch or flatten an object to such an extreme degree. Furthermore, it displayed a complete lack of the classic cometary features. As most comets approach the sun, their icy surfaces heat up, vaporizing and releasing gas and dust that form a visible atmosphere or coma, and often a tail. ʻOumuamua had no coma, no tail, and no detectable outgassing whatsoever. It appeared, for all intents and purposes, to be a dark, inert, and strangely shaped rock. Then came the real curveball. As ʻOumuamua sped away from the sun, astronomers meticulously tracked its path. They found that it was not following a purely gravitational trajectory. Something was giving it an extra, tiny but consistent push, a non-gravitational acceleration that was gently altering its course. This is a common phenomenon for comets, as jets of gas acting like small thrusters can push them off course. But ʻOumuamua showed no visible signs of this outgassing. This discrepancy between what was observed, no coma, and what was measured, an acceleration, became the central enigma of the entire event. How could an object be accelerating without any visible evidence of the propellant causing it? This is where the scientific debate truly ignited, producing a spectrum of theories from the conventional to the highly speculative. The leading natural explanation proposes that ʻOumuamua was, in fact, a comet, but a very exotic one. One compelling idea is that it could have been a hydrogen iceberg. In the coldest, densest cores of giant molecular clouds, hydrogen gas can freeze solid. A chunk of this frozen hydrogen, ejected from its system, would have begun to sublimate or turn directly from a solid to a gas under the heat of the sun. Hydrogen gas is extremely difficult to detect with our telescopes, and its release would provide just the right kind of gentle push to explain the acceleration without producing a visible dusty coma. Another natural theory suggests it could be a nitrogen iceberg, a fragment torn from a Pluto-like object in a distant solar system, with nitrogen ice sublimating in a similarly stealthy manner. The unusual acceleration and shape also opened the door, cautiously, to more extraordinary possibilities. Could Oumuamua be a piece of alien technology? The most famous proponent of this idea, Harvard astronomer Avi Loeb, suggested that the object's flat profile and the specific nature of its non-gravitational push were consistent with a light sail, a thin, reflective sheet designed to be propelled by the radiation pressure from starlight. In this hypothesis, Oumuamua wasn't a natural rock but a discarded piece of an advanced civilization's technology, perhaps a broken-off piece of a larger probe drifting through the galaxy. While the vast majority of the scientific community favors a natural origin, citing Occam's razor the principle that the simplest solution is usually the correct one, this debate highlighted how ill-prepared we were to analyze such an object and how even outlandish ideas can stimulate important scientific discussion. Regardless of its true nature, Oumuamua's brief visit was a monumental wake-up call for astronomy. It proved that interstellar objects are passing through our solar system with some frequency. We simply hadn't had the surveying tools to detect them. This visitor carried with it the untold secrets of its home system, a system we will never directly visit. Its composition, structure, and history held clues about how planets and other bodies form around other stars, offering a rare piece of physical evidence from beyond our sun's influence. Its passage has since spurred a dedicated effort to find more of these interstellar travelers. Projects like the upcoming Vera-C Rubin Observatory are designed to scan the entire sky with unprecedented depth and frequency, ensuring we don't miss the next Oumuamua. When the next one arrives, we will be ready to point every telescope we have at it, studying its spectrum, shape, and behavior from the moment it enters our neighborhood, hoping to finally understand the true nature of these silent messengers from the cosmic ocean. Amidst the cosmic violence of gamma-ray bursts and the silent drift of rogue planets, the search for extraterrestrial intelligence often feels like a patient, listening vigil. And on one extraordinary evening in the summer of 1977, that vigil may have paid off in the most tantalizing way imaginable. The story begins with the Big Ear radio telescope at Ohio State University, a workhorse instrument methodically scanning the skies as part of the ongoing search for extraterrestrial intelligence, or SETI. Its operation was largely automated, with computers logging the signal strength across 50 channels of the radio spectrum, and it was volunteer Jerry Amon who was tasked with the mundane job of sifting through the reams of printed data days later. But on August 15th, he came across a sequence of alphanumeric codes that made him stop cold. There, circled in red pen, was a string of characters representing a signal so powerful and so perfectly crafted that it defied any easy explanation. In the margin, Jerry Amon simply wrote, "Wow, what made this signal so remarkable was its precise signature, a signature that aligned perfectly with what theorists predicted an intentional interstellar broadcast would look like." It was a strong, narrowband signal concentrated on one specific frequency, the hydrogen line at 1420 MHz. Hydrogen is the most abundant element in the universe, and this quiet frequency band is relatively free of natural cosmic background noise, making it a logical choice for any civilization trying to get noticed. The signal also exhibited the telltale rise and fall in intensity over exactly 72 seconds, the precise duration the Big Ear telescope could focus on a fixed point in the sky as the Earth rotates. This wasn't a random burst of static. It behaved exactly as a signal from a distant, fixed source should, appearing from nowhere, peaking, and then fading away with mathematical perfection as the telescope's beam moved on. It came from the direction of the constellation Sagittarius, a region crowded with stars, and for that brief window, it was the loudest thing in the sky. The immediate and enduring mystery is that the WOW signal was a one-off event. Despite decades of dedicated follow-up observations by Eamon and countless other astronomers, listening to the same patch of sky with ever more sensitive equipment, the signal has never been heard again. It was a cosmic shout that vanished into silence, a single, perfect note played just once. This singular nature is what fuels both the scientific intrigue and the public fascination. If it was a deliberate broadcast, why was it never repeated? Was it a brief, targeted beacon not meant for us that we just happened to intercept? Or was it something else entirely, a fleeting natural phenomenon we still don't fully understand? Over the years, numerous attempts have been made to find a natural explanation. Some have proposed it was a signal reflected off a piece of space debris in our own solar system, though the specific frequency and profile make this unlikely. A more recent theory, put forward in 2020, suggested the signal could have been generated by a hydrogen cloud surrounding a comet that happened to be passing through that region of the sky at the time. However, this explanation has been heavily scrutinized and largely dismissed by astronomers, who point out that comets do not emit strong, narrowband radio signals of this nature, and the specific comets proposed weren't even in the right part of the sky when the signal was detected. The comet hypothesis, while a valiant effort, has failed to solve the puzzle, leaving the WOW signal's origin as mysterious as ever. The legacy of those 72 seconds extends far beyond a single circled printout. The WOW signal became a cultural touchstone and a powerful symbol for the SETI Institute and similar endeavors around the world. It is a reminder that perseverance is paramount in a search where success might come only once in a lifetime, or even once in a century. It demonstrated that our equipment and our methods were capable of recognizing a potentially artificial signal if one ever arrived, validating the entire scientific approach. This one unconfirmed event continues to inspire new generations of scientists to build more powerful radio telescope arrays and develop more sophisticated algorithms to sift through the cosmic noise, always hoping to find another signal, perhaps one that lasts long enough for us to answer back. It stands as a monument to human curiosity, a quiet but persistent question mark in the sky that challenges our assumption that we are alone and fuels our deepest wonder about who or what might be out there listening. After contemplating the silent, drifting worlds and the fleeting, unexplained signals, we arrive at a mystery that is perhaps the most profound of all because it forces us to confront not just the universe, but our own place within it. This is the Fermi paradox, the staggering and unsettling contradiction between the universe's immense potential for life and the utter silence we hear in return. The numbers are overwhelmingly on the side of existence. Our Milky Way galaxy alone contains hundreds of billions of stars, and a significant fraction of those are now believed to host planets orbiting within their habitable zones. The so-called Goldilocks region where conditions might be just right for liquid water, and by extension, life as we know it. With the universe being nearly 14 billion years old, there has been more than enough time for intelligent civilizations to arise, develop advanced technology, and spread across the galaxy. The mathematics suggests the cosmos should be teeming with life, a vibrant interstellar community. And yet, when we train our radio telescopes on the heavens, we are met with a profound and puzzling quiet. The question, first posed informally by physicist Enrico Fermi during a lunch conversation in 1950, cuts to the heart of the matter. If they are out there, then where is everybody? The power of this paradox lies in its ability to generate a spectrum of potential solutions, each more thought-provoking than the last, and they generally fall into two broad categories. The first set of answers suggests that we are not hearing anything because there is, in fact, no one else out there to talk to. This is a deeply humbling possibility. It could be that while simple microbial life might be common, the emergence of complex, multicellular, and ultimately intelligent life requires such a precise and unlikely series of evolutionary leaps that it is an extraordinarily rare event in the cosmos. This concept is often explored through the idea of the Great Filter, a hypothetical barrier that prevents life from progressing to a spacefaring stage. The frightening implication is that this filter might not be behind us. It could still lie ahead. Perhaps the development of advanced technology, such as artificial intelligence or nuclear weaponry, inevitably leads to a civilization's self-destruction. In this grim scenario, the silence we hear is the echo of countless civilizations that have already risen and fallen, a cosmic graveyard of unfulfilled potential. The second category of solutions proposes that other civilizations do exist, but for one reason or another, we cannot perceive them or they are choosing not to make contact. Perhaps interstellar travel is far more difficult and energy-intensive than we imagine, effectively isolating every civilization on its own island world. Maybe advanced species communicate through technologies we haven't even begun to conceive of, using neutrinos or gravitational waves instead of radio, making their conversations invisible to our primitive ears. There are also more philosophical and slightly unsettling answers. The zoo hypothesis suggests that Earth is being intentionally left alone as a kind of cosmic wildlife preserve or a sociological experiment, observed from a distance by galactic anthropologists who adhere to a strict policy of non-interference. Alternatively, we might be living in a galactic backwater, an uninteresting region that more established civilizations have already explored and moved on from, leaving us in a quiet, undeveloped corner of the spiral arm. This paradox does more than just inspire fascinating speculation. It actively shapes our scientific endeavors. The ongoing search for extraterrestrial intelligence through projects like SETI is a direct response to Fermi's question, a systematic effort to comb through the radio silence for any faint whisper of an artificial signal. At the same time, missions like the James Webb Space Telescope are addressing the other side of the equation, searching for biosignatures, chemical imbalances in the atmospheres of distant exoplanets that could be indicative of biological processes, even if just of the microbial variety. Finding simple life elsewhere would be a monumental discovery, but it would also intensify the Fermi paradox. If life starts easily but intelligence is nowhere to be found, the notion of a great filter looming in our future becomes even more pressing. Ultimately, the Fermi paradox holds up a mirror to humanity, forcing us to reflect on our own trajectory and longevity. It underscores the precious fragility of our own existence and the profound responsibility that comes with our technological adolescence. The silence is not necessarily a sign of loneliness, but perhaps a lesson, a warning to navigate our future with wisdom and caution if we hope to one day become the answer to another civilization's paradox, rather than just another data point in the great cosmic silence. This contemplation of our own rarity and vulnerability naturally leads us to wonder what kind of strange and exotic environments might actually host life, pushing our search beyond the familiar. For decades, our search for life beyond Earth has been guided by a single, powerful image, a pale blue dot, a world of continents and oceans under a nitrogen-rich sky, orbiting comfortably within a star's habitable zone. This Earth-centric view has defined our concept of where life could thrive, but the universe has a way of shattering our parochial expectations, revealing possibilities far stranger and more wonderful. Enter the Hycean world, a revolutionary concept that completely reimagines the very definition of a habitable planet. Picture a world significantly larger and hotter than our own, a mini Neptune shrouded in a thick, global atmosphere dominated by hydrogen gas. Beneath this immense pressurized blanket, not of rock but of a planet-wide, superheated ocean of liquid water, deeper than any on Earth could exist. These are not planets as we know them. They are steamy, dark water worlds where the sky is a perpetual, crushing haze, and the notion of a shoreline is a foreign concept. It's a vision that sounds like it belongs in the realm of science fiction, yet it is a serious, compelling hypothesis that is dramatically expanding the cosmic real estate we consider worth investigating for signs of life. The term Hycean itself is a portmanteau, blending the words hydrogen and ocean, and it was first proposed by a team of astronomers at the University of Cambridge only recently. Their groundbreaking insight was to realize that a planet does not need to be a rocky twin of Earth to possess the fundamental ingredient for life, a stable, long-lived liquid water ocean. On a Hycean world, the thick hydrogen atmosphere acts as a powerful insulator and a pressurizing agent. Even though these planets may orbit much closer to their dim red dwarf stars than Earth does to the Sun, receiving far more stellar radiation, the immense atmospheric pressure prevents the ocean from boiling away into space. Conversely, the atmosphere is so effective at trapping heat that even on a Hycean world drifting on the outer, colder edges of the habitable zone, the ocean would be kept liquid by the planet's own internal warmth, much like the subsurface ocean on Jupiter's moon Europa. This dual mechanism means the traditional Goldilocks zone is suddenly much wider and more accommodating, encompassing a whole new class of previously overlooked planets. What makes this idea so electrifying for astrobiologists is the sheer abundance of potential Hycean worlds. Our surveys have already revealed that mini Neptunes are among the most common type of planet in our galaxy, especially around the plentiful red dwarf stars. For years, these planets were largely written off in the search for life. Their large size and gassy compositions suggested they were simply smaller versions of Neptune, with no solid surface and temperatures and pressures far too extreme for biology. The Hycean hypothesis completely overturns that dismissal. It suggests that thousands of worlds we had already discovered and previously excluded from our life hunting lists might be prime candidates after all. We may have been sitting on a treasure trove of habitable ocean planets without even realizing it. The real test, of course, is not just theorizing about their conditions, but actually probing their atmospheres for the chemical fingerprints of biological activity, known as biosignatures. This is where our technological prowess comes into play. The James Webb Space Telescope, with its unparalleled infrared sensitivity, is the perfect tool for this detective work. The thick hydrogen atmosphere of a Hycean world, while opaque to visible light, is actually relatively transparent in the infrared, allowing JWST to peer deep into its atmospheric layers as the planet transits in front of its star. Scientists are not just looking for the familiar signs of oxygen and methane, which might be produced differently in such an environment. They are developing a new toolkit of biosignatures specifically for these exotic worlds. Key among them are methyl chloride and dimethyl sulfide gases that on Earth are produced primarily by marine phytoplankton. The detection of such molecules in the hydrogen-rich atmosphere of a Hycean world would be a breathtakingly strong hint that something is living in that global, dark ocean. Of course, the environment on a Hycean world would be utterly alien. any life there would have to contend with crushing pressures, no sunlight whatsoever, and a chemistry based in a hydrogen-rich environment rather than our nitrogen-oxygen mix. Yet we know from extremophiles on Earth that life is incredibly resilient and inventive. Microbes thrive in the boiling vents at the bottom of our oceans, in acidic lakes, and in rocks deep underground. The concept of life finding a way in the dark, hot depths of a Hycean ocean, perhaps around hydrothermal vents on the seafloor, is not just plausible, it might even be common. The study of these hypothetical worlds is more than just adding a new category to our exoplanet catalog. It is a fundamental shift in perspective. It teaches us to let go of our Earth-biased assumptions and embrace the true diversity of worlds that the universe has to offer, reminding us that life, if it exists out there, will likely be far weirder and more wonderful than we ever dreamed. While we search for life on exotic Hycean worlds, a different kind of mystery was unfolding around a seemingly ordinary star over 1,000 light-years away, one that would capture the world's imagination and challenge our very understanding of what might be possible. This is the story of Tabby's star, officially known as KIC 8462852, a sun-like star in the constellation Cygnus that behaves like no other we have ever seen. Its claim to fame is not what it emits, but what it obscures. This star undergoes dramatic, irregular, and utterly perplexing dips in its brightness, dimming by as much as 22% at times, a staggering amount when you consider that a gas giant the size of Jupiter passing in front of it would only cause a 1% dip. It's as if something colossal and strangely shaped is moving in front of it, blocking its light in a way that defies all conventional explanation, turning a routine data stream from the Kepler Space Telescope into one of the greatest astrophysical detective stories of the century. The discovery of this bizarre behavior is a perfect example of how modern science often works, relying on both advanced technology and the collective power of human curiosity. The Kepler mission was designed to find exoplanets by staring at thousands of stars and looking for the tiny, periodic dimming caused by planets transiting their faces. In 2015, a team of citizen scientists, part of the Planet Hunters project, were sifting through Kepler's public data when they flagged this particular star as being deeply weird. It was later named after the lead author of the paper investigating it, astronomer Tabetha Boyajian. The initial data revealed not the clean, symmetrical dips of a planet, but a series of deep, jagged, and asymmetric declines in brightness. Some dips were shallow and long-lasting, while others were sharp and profound, with no discernible pattern or predictable periodicity. It was clear from the start that we were not looking at a planet or even a family of planets. We were looking at something entirely new. When faced with such an anomaly, the scientific method demands that we first exhaust all known natural explanations before venturing into the unknown. The leading hypothesis, and the one most astronomers consider the most likely, involves dust. A massive, uneven cloud of fine dust and debris orbiting the star could account for the irregular dimming patterns. Dust is excellent at blocking light, and its particles can be distributed in complex, clumpy formations that would cause the star's brightness to flicker and fade in the strange ways we observe. The source of this dust could be a catastrophic collision in the star's asteroid belt, the breakup of a giant comet or even a moon, or a family of shattered planetary bodies creating a vast, swirling disk of debris. The key evidence supporting this idea came from follow-up observations which showed that the dimming was more pronounced at blue wavelengths than at red ones. This is a classic signature of starlight scattering off tiny dust particles, which tend to block blue light more effectively, much like our own sky appears blue because of how sunlight scatters in the atmosphere. However, the sheer scale and irregularity of the dimming events pushed the boundaries of even these dramatic natural explanations, opening the door, however cautiously, to a more speculative and thrilling possibility. Could we be witnessing the construction of a megastructure? The most famous of these theoretical constructs is a Dyson sphere, a hypothetical swarm of giant solar collectors built by an advanced civilization to harness the entire energy output of its star. Such a structure would not be a solid shell, but a dense network of orbiting platforms that would block starlight in irregular, non-periodic ways, much like what we see with Tabby's star. This idea, while considered far less probable by most astronomers, captured the public's imagination like few other scientific stories, transforming a technical anomaly into a global conversation about our place in the universe and the potential for other intelligent life. This public fascination had a direct and positive impact on the science. When traditional telescope time was insufficient to monitor the star continuously, Tabitha Boyajian and her colleagues launched a highly successful Kickstarter campaign, raising over $100,000 from thousands of backers around the world to fund a dedicated ground-based observing campaign. This allowed them to secure time on a global network of telescopes, ready to spring into action the moment the star began dimming again. This model of public engagement showcased a new way of doing science, where citizen scientists and crowdfunding could play a vital role in investigating real-time cosmic mysteries. The continued monitoring has further reinforced the dust hypothesis, with detailed studies of the dimming patterns consistently pointing toward a natural, if extraordinarily complex, circumstellar environment. The true legacy of Tabby's star is not that it provided evidence for aliens, but that it demonstrated the power of an open mind and the importance of investigating anomalies without preconceived notions. It forced astronomers to develop new models for stellar behavior and planetary system disruption, enriching our understanding of how chaotic and variable young solar systems can be. It serves as a powerful reminder that the universe is still full of surprises, and that sometimes the most valuable scientific discoveries are the ones we cannot immediately explain. This single, puzzling star reminds us to expect the unexpected, a lesson that prepares us for the next great mystery hidden in the vast emptiness between the galaxies. After exploring the dynamic violence of stellar explosions and the silent drift of rogue planets, we now turn our attention to a realm defined not by what is there, but by what is profoundly, overwhelmingly absent. Welcome to the Boötes Void, a place astronomers have nicknamed the Great Nothing. This is not a mere empty pocket between stars. It is a staggering spherical chasm in the fabric of the universe, a void so immense it could comfortably contain thousands of galaxies like our Milky Way, yet it holds almost none. Stretching an almost incomprehensible 330 million light-years across, this region of space is one of the largest known structures in the entire cosmos, a gaping hole in the cosmic web that challenges our deepest theories about how the universe organized itself after the Big Bang. The story of its discovery in the early 1980s is a testament to the painstaking work of mapping the cosmos. Astronomer Robert Kirshner and his team were conducting a redshift survey, meticulously measuring the distances to galaxies to create a three-dimensional map of our corner of the universe. As they pieced the data together, they encountered a vast region in the direction of the constellation Boötes that was eerily, inexplicably blank, where the surrounding areas were filled with the brilliant points of light from galaxy clusters and filaments. This zone was a desert of unprecedented scale. The initial survey found only a handful of galaxies in this enormous volume where standard models predicted there should be thousands. It was as if they had stumbled upon a spherical room in a crowded mansion that was almost completely empty, a discovery that sent ripples of surprise and curiosity through the cosmological community. This profound emptiness presents a significant challenge to our models of structure formation. The prevailing theory of the universe's evolution, known as the lambda cold dark matter model, does predict that gravity will pull matter into dense filaments and clusters, leaving behind underdense voids. However, the sheer scale of the Boötes void pushes the limits of what this model can comfortably explain. It is so large and so empty that it seems to require either a series of extraordinarily unlikely cosmic mergers, where smaller voids combined into one gigantic one, or perhaps hints at physics we don't yet fully understand. Some theorists have even playfully, though not entirely seriously, suggested it could be the imprint of a collision with a parallel universe in the multiverse, though most scientists seek explanations within our standard physics, just pushed to its extremes. Studying this great nothingness is crucial because voids are not passive empty spaces. They are active players in the evolution of the cosmos. The incredibly low density of matter inside a void like Boötes means that the expansion of the universe proceeds faster there than in the crowded galactic clusters. The gravitational pull of matter is weaker, so dark energy, the mysterious force accelerating the universe's expansion, has a more dominant effect. By precisely measuring the size, shape, and growth of these voids through ambitious projects like the Dark Energy Survey, astronomers can use them as precision tools to measure the strength of dark energy and the properties of dark matter. The void acts as a natural laboratory, its emptiness providing a clean backdrop against which to test the fundamental forces shaping all of reality. The few galaxies that do persist within this vast desert are themselves fascinating subjects. Isolated from the frequent galactic collisions and interactions that shape galaxies in clusters, these lonely islands of stars evolve in near total solitude. They are like castaways on a cosmic raft, their development dictated by their own internal processes rather than the influence of neighbors. Studying these isolated galaxies helps astronomers understand the baseline of galactic evolution, free from the complicating factors of mergers and close encounters. Their very existence in such a hostile environment also tells us something about the initial conditions of the universe. Somehow, tiny seeds of matter persisted in this region even as the gravitational tide pulled most everything else away. The true power of the Boötes void, however, lies in the profound perspective it offers. To consider this scale of emptiness is a humbling experience. If you were located on a planet at the center of this void and you looked up at the night sky, you would see a profound and absolute blackness. With no nearby galaxies to speak of, the sky would be almost entirely empty, the distant glow of the cosmic web barely perceptible. It is a vision of terrifying isolation, a stark contrast to our own rich vantage point within a vibrant galactic cluster. This great nothing forces us to confront the sheer scale of the universe, a place that is not uniformly filled with brilliant lights, but is instead a patchwork of vibrant cities of galaxies separated by deserts of staggering, mind-numbing emptiness. This contemplation of the vast structures, both full and empty, that make up our universe naturally leads us to question one of cosmology's most fundamental principles. Just when we think we have a fundamental grasp on the universe's structure, a discovery comes along that seems to challenge the very bedrock of modern cosmology. This brings us to one of the most intriguing and controversial puzzles in all of astronomy, an enigma so profound it has been dubbed, with a hint of dramatic flair, the axis of evil. This is not a malevolent force, but a mysterious and unexpected pattern found in the oldest light we can see, the cosmic microwave background radiation. This faint afterglow, the cooled remnant of the Big Bang itself, is supposed to be the ultimate snapshot of a newborn universe that was smooth, uniform, and without any preferred direction. It is the strongest evidence we have for the cosmological principle. the foundational idea that on the largest scales, the universe is homogeneous and isotropic, meaning it looks the same in every direction and from every location. The existence of an axis within this primordial light would suggest a startling deviation from this core principle, hinting that the universe might have a fundamental orientation, a preferred direction that should not exist. The story of this discovery begins with the Wilkinson Microwave Anisotropy Probe, or WMAP, a NASA spacecraft launched in 2001 with the ambitious goal of mapping the minute temperature fluctuations in the cosmic microwave background with unprecedented precision. These tiny variations on the order of 100,000th of a degree are the seeds from which all the galaxies, stars, and planets eventually grew. When scientists analyzed the magnificent full sky map produced by WMAP, they found the overall data beautifully supported the standard model of cosmology. But upon closer inspection, a few stubborn anomalies refused to fit the neat picture. The most perplexing of these was an unexpected alignment. Certain large-scale patterns in the temperature fluctuations, the very hot and cold spots that dot the early universe, seemed to be correlated across vast distances in a way that suggested they were oriented along a particular axis that runs through our solar system. It was as if the universe had a subtle equator, and this alignment became informally known as the axis of evil. Naturally, the scientific community was deeply skeptical. The immediate and most logical assumption was that this was some kind of systematic error, an unaccounted for foreground contamination from our own Milky Way galaxy, an imperfection in the instrument's calibration, or perhaps an effect introduced during the complex data processing needed to translate raw readings into a clean map of the early universe. The hope was that the next-generation mission, the European Space Agency's Planck satellite, which launched in 2009 with even greater sensitivity and resolution, would resolve the issue and make the anomaly disappear. But when the Planck team released their exquisite high-fidelity map of the cosmic microwave background, the axis of evil did not vanish, it persisted. While some of its specific features were less pronounced, the strange alignment and other large-scale anomalies, like an unexplained cold spot and a curious hemispheric asymmetry, remained stubbornly present in the data. This forced everyone to take the mystery much more seriously. The possibility that it was merely a fluke or a data artifact became harder to sustain. If this axis is indeed real and not a ghost in the machine, the implications are truly revolutionary, pointing to physics beyond our current understanding. One extraordinary possibility is that this preferred direction is a cosmic fossil, an imprint from the era before the Big Bang. Some theories of quantum gravity suggest that the universe we see is just one part of a larger multiverse, and that the axis of evil could be a bruise left from a collision with another universe in this vast cosmic foam. Alternatively, it could indicate that the fundamental laws of physics themselves are not perfectly uniform across the cosmos, but very slightly depending on direction, a concept that would require a complete overhaul of our most cherished theories. Even the nature of dark energy, the mysterious force accelerating the universe's expansion, has been questioned. Could its strength be slightly different in one direction than another, creating a subtle tilt in the fabric of space-time? These are not ideas put forward lightly. They are the kind of radical rethinking that occurs when nature presents us with data that refuses to conform to our elegant models. The debate surrounding the axis of evil is a perfect example of the scientific process at work, a careful, sometimes tense, dance between extraordinary evidence and extraordinary claims. The majority of cosmologists still maintain a healthy caution, diligently searching for any overlooked systematic effect that could explain the alignment. Yet, its persistence across 2 major space missions ensures it cannot be simply ignored. It stands as a quiet but persistent challenge to our cosmic arrogance, a reminder that for all our magnificent achievements in mapping the universe, we may still be missing a fundamental piece of the puzzle. This anomaly doesn't just ask us to tweak a few equations. It urges a profound re-evaluation of our place in the cosmos and the very principles we believe govern it, pushing our curiosity toward the ultimate question of where everything began. For nearly a century, one number has reigned supreme in cosmology, a single figure that defines the very expansion of the universe and our place within it, the Hubble constant. It represents the rate at which the cosmos is stretching, the speed at which galaxies are receding from us for every megaparsec of distance. Pinpointing this number accurately is the closest thing cosmology has to a holy grail, as it tells us the age of the universe, its ultimate fate, and governs the scale of everything we see. For decades, astronomers have worked to measure it with ever greater precision, confident that different methods would eventually converge on a single, universal truth. But instead of converging, something deeply unsettling has happened. 2 of the most trusted and precise methods for measuring this fundamental constant have begun to disagree, and the gap between them is not shrinking, it's growing. This stubborn and escalating conflict is what cosmologists now call the Hubble tension, and it is one of the most significant puzzles in modern science, a crack in the foundation of our understanding that suggests we might be missing something profound about how the universe works. On one side of this debate, we have the cosmic archaeologists. These scientists look back to the very beginning, using the afterglow of the Big Bang itself, the cosmic microwave background, as their time machine. By meticulously mapping the tiny temperature fluctuations in this ancient light with satellites like Planck, they can read the conditions of the infant universe. They see the precise blueprint of how matter was distributed, and from that, they can calculate how fast the universe must have been expanding to create the structures we see today. This is a powerful, physics-based approach that relies on our well-tested model of the cosmos, known as the lambda cold dark matter model. The answer it gives for the Hubble constant is incredibly precise, approximately 67.4 kilometers per second per megaparsec. This means that for every megaparsec of distance, about 3.26 million light-years, a galaxy is moving away from us 67.4 kilometers per second faster. On the other side are the cosmic surveyors, the stellar cartographers who measure the universe as it is today. Their gold standard method involves a specific type of stellar explosion, type 1, a supernova. These are known as standard candles because they all explode with nearly the same intrinsic brightness. By measuring how bright they appear from Earth, astronomers can calculate their distance with remarkable accuracy. When they combine this distance with measurements of how fast the supernova's host galaxy is moving away from us, they can directly calculate the Hubble constant. This is a straightforward, distance ladder approach, a step-by-step measurement that doesn't rely on a grand cosmological model. Teams using this method, along with other local techniques like observing pulsating stars called Cepheid variables, consistently arrive at a higher number, around 73 kilometers per second per megaparsec. At first glance, a difference of about 5.6 units might not seem like much, but in the world of precision cosmology, where measurements are made with uncertainties of less than 1%, this gap is a yawning chasm. The discrepancy now stands at a confidence level of 4 to 5 sigma, meaning there is only a 1 in 100,000 to 1 in 1 million chance that this is a mere statistical fluke. It is a real disagreement, a persistent and growing headache for cosmologists that refuses to go away despite years of rechecking data, hunting for errors, and refining techniques. This isn't just a minor accounting error. It's a fundamental mismatch between the story of the universe's infancy and the story of its present day. So what could possibly explain this tension? Scientists are exploring two broad possibilities. The first, and perhaps less exciting, is that there is an unaccounted for systematic error in one of the measurements. Maybe our understanding of the physics of Cepheid variables or supernova is subtly flawed. Perhaps there is some unknown dust or population of stars in galaxies that is skewing the local distance measurements. Teams are working tirelessly to root out these potential errors, but so far, none have been found that can fully bridge the gap. The second, and far more thrilling possibility, is that the tension is real and points toward new physics beyond our current standard model of cosmology. Our model might be incomplete. One leading idea is a concept called early dark energy. This proposes that in the very first few 100,000 years after the Big Bang, there was an additional, transient form of dark energy that gave the universe a little extra push, accelerating its expansion for a brief period before vanishing. This would affect the Planck measurements of the early universe but would not be factored into the local, present-day measurements, neatly explaining the discrepancy. Other theories suggest modifications to Einstein's theory of gravity itself on the largest scales, or that dark matter has properties we haven't yet discovered. The resolution of this mystery is a primary goal for our newest and most powerful observatories. The James Webb Space Telescope, with its razor-sharp infrared vision, is now turning its gaze to the Cepheid variables and supernova used in the local measurement, aiming to remove any doubt about the calibration of the cosmic distance ladder. Its data will either confirm the higher local value with unassailable precision or finally identify a hidden systematic error. Meanwhile, next-generation projects like the Vera C. Rubin Observatory will discover thousands more supernova, providing a colossal new dataset to analyze. Solving the Hubble tension is about far more than just agreeing on a number. It is a direct pathway to unlocking deeper secrets. If the cause is indeed new physics like early dark energy, it would revolutionize our understanding of the fundamental forces that have shaped the cosmos. It would tell us that the dark energy driving the universe's acceleration today is not a constant, but something that could evolve and change, with dramatic implications for the ultimate fate of everything. This conflict in our most trusted data is a powerful reminder that the universe still holds profound surprises, and that our quest to understand it is a dynamic, evolving story where even our most fundamental constants are open for debate. As we move from the grand tensions of cosmic expansion to the intricate details of the early universe, we encounter a mystery that proves even the smallest discrepancy can have the most profound implications. This is the lithium problem, a puzzle that takes us back to the very first minutes of existence, when the entire cosmos was a seething nuclear furnace. According to our beautifully precise models of Big Bang nucleosynthesis, the process that forged the first light elements, the universe should have created a specific amount of lithium alongside hydrogen and helium. The calculations are exquisitely detailed, factoring in the universe's expansion rate, density, and the known cross-sections of nuclear reactions. Yet, when we look out at the oldest stars in our galaxy, the pristine stellar relics that formed from nearly pure Big Bang material, we find a glaring inconsistency. The amount of lithium-7 we observe is only about 1/3 of what our theories so confidently predict. It's as if a crucial ingredient in the recipe of creation has gone mysteriously missing, a cosmic oversight that has persisted for over 13 billion years. This isn't a minor accounting error. It's a fundamental crack in our understanding of the universe's first moments. The predictions for the other light elements deuterium, helium-3, and helium-4 match the observed abundances almost perfectly, which is why Big Bang nucleosynthesis is considered one of the three pillars of evidence for the standard model of cosmology. The success with those elements makes the lithium shortfall all the more perplexing. It suggests that our model is overwhelmingly correct, but that there is a subtle piece of physics we are missing, something that specifically affected the production or survival of lithium and nothing else. This tiny anomaly forces us to question whether our knowledge of nuclear physics in those extreme early conditions is truly complete. Perhaps the cross-sections, the probabilities of certain nuclear reactions occurring, are slightly off. Or maybe there were unknown nuclear pathways or rare particles present that could have destroyed lithium as quickly as it formed. One fascinating line of inquiry suggests the solution might not lie in the first few minutes, but in the billions of years that followed. Could the lithium have been there initially, only to be slowly destroyed within the stars themselves? The oldest stars we observe are, by their nature, incredibly long-lived and have had ample time to process the material in their outer layers. Some theories propose that lithium could be gradually dragged from the surface down into the hotter interior of these stars, where temperatures are so high that the fragile lithium nuclei would be instantly torn apart by nuclear reactions. Other ideas involve the gentle convection currents within these stellar atmospheres, or even the presence of waves that could mix the layers and destroy the element. If such depletion mechanisms are at work, then the oldest stars are not the pristine time capsules we believe them to be, and we would need to find new ways to peer back to the true initial conditions. The search for answers has pushed experimental physics to its limits. Scientists are now using powerful particle accelerators to recreate the incredible energies of the infant universe, attempting to measure the key nuclear reaction rates with far greater precision than ever before. Even a tiny revision in one of these numbers could be enough to resolve the discrepancy. At the same time, astronomers are on a cosmic scavenger hunt, searching for the most metal-poor stars imaginable, those with the absolute smallest contamination from later generations of elements. Finding a star with even less lithium than the already low norm would be a bombshell, strongly supporting the stellar depletion idea. Conversely, finding a star that perfectly matches the predicted amount would be equally revolutionary, suggesting that our current samples are somehow atypical. The implications of solving this puzzle extend far beyond just accounting for one element. Lithium is a key piece of the cosmic puzzle, and understanding its true history would provide a crucial test for the standard model of particle physics and cosmology. It could even point toward new, exotic physics, such as the influence of unknown particles that were present in the early universe and interacted with nuclear processes. The lithium problem is a powerful reminder that science often advances not when our theories are proven right, but when they are proven just slightly wrong, creating a beautiful and productive tension that drives us toward a deeper, more complete truth. This investigation into the fundamental building blocks of matter seamlessly guides us to consider other anomalies closer to home within our own solar system. While we often picture the vastness of space as a perfect, frictionless void where a spacecraft, once set in motion, should glide forever, the real universe is full of subtle, complex forces that can gently tug and push on an object over immense distances. This brings us to one of the most fascinating detective stories in the history of space exploration, the Pioneer anomaly. For decades, this tiny, persistent mystery, a slight, unexplained deceleration acting on two intrepid robotic explorers, captivated and confounded physicists, pushing them to consider everything from new laws of gravity to invisible halos of dark matter, all before arriving at a solution that was hiding in plain sight, a brilliant lesson in the devilish details of engineering and the relentless pursuit of precision. The story centers on the Pioneer 10 and 11 spacecraft, true pioneers that were the first to venture through the asteroid belt and the first to make close-up observations of Jupiter and Saturn. After completing their primary missions in the late 1970s, these hardy probes continued on their trajectories, speeding toward the outer reaches of the solar system and eventually into the boundless realm of interstellar space. As they did, teams at NASA meticulously tracked their positions using the Deep Space Network, measuring the tiny Doppler shift in their radio signals to determine their velocity with astonishing accuracy. And that's when they noticed something was off. Both spacecraft were experiencing a constant sunward deceleration, an incredibly faint but undeniable pull back toward the Sun that was about 10 billion times weaker than the gravity we feel here on Earth. To put it in perspective, it was equivalent to the gravitational pull of a single penny from a distance of about 2,000 miles. Minuscule, yes, but over the course of a year, this effect would cause the spacecraft to lag behind their predicted positions by thousands of miles, a discrepancy that could not be ignored. For nearly 30 years, this anomaly was a thorn in the side of cosmologists. The most exciting explanations were, of course, the most revolutionary. Could this be our first tangible evidence of a local concentration of dark matter in our solar system, a halo of invisible particles exerting an extra gravitational drag on the probes? Or did it point to a flaw in our understanding of gravity itself? Perhaps Einstein's theory of general relativity needed a slight modification on the largest scales, a tweak that would account for this unexpected pull. These were thrilling possibilities, suggesting that a simple tracking anomaly could be the key to unlocking profound new physics. The Pioneer anomaly became a celebrated puzzle, a symbol of how even our most successful missions can reveal gaps in our fundamental knowledge. The true resolution, however, turned out to be a masterclass in Occam's razor, the principle that the simplest explanation is often the correct one. A dedicated team of researchers, led by Slava Turyshev, embarked on a monumental forensic investigation. They painstakingly recovered decades-old data stored on archaic magnetic tapes and old-fashioned punch cards, and even tracked down retired engineers to reconstruct the spacecraft's original blueprints and operational histories. Their breakthrough came when they realized the answer wasn't in the void of space, but in the very heart of the probes themselves, their power sources. The Pioneer spacecraft were powered by radioisotope thermoelectric generators, which produced electricity from the heat of decaying plutonium. This heat had to be radiated away into space to prevent the spacecraft from overheating. The team built an incredibly detailed thermal model of the spacecraft and discovered that this radiation of heat was not perfectly symmetrical. A slightly greater proportion of heat was being emitted from the back of the spacecraft's main antenna dish, which faced toward the Sun. This created a tiny but constant recoil force, a photon thrust pushing the spacecraft back toward the Sun, exactly mimicking an anomalous gravitational pull. The meticulous accounting of this thermal radiation pressure finally solved the mystery, closing one of the longest-running chapters in space science. But the legacy of the Pioneer anomaly is far greater than its solution. It stands as a powerful testament to the critical importance of metrology, the science of measurement in deep space exploration. The fact that we could even detect such an infinitesimally small force across billions of miles is a triumph of human ingenuity. The lessons learned have been directly applied to every mission that has followed, especially those requiring ultra-precise navigation like the New Horizons flyby of Pluto and the ongoing Voyager missions. Engineers now meticulously model the thermal emissions and even the tiny forces from outgassing from a spacecraft's materials to account for every possible nudge. This historical puzzle reminds us that the universe often speaks in whispers, not shouts, and that solving its greatest mysteries requires not just grand theories, but an unwavering commitment to the smallest details, a principle that guides us as we turn our attention to the very edge of our own planetary system. Just when we think we have our own cosmic backyard mapped out, the solar system throws us another curveball, a mystery lurking right at the very edge of our planetary neighborhood. We've journeyed to the farthest reaches past the orbit of Neptune into a vast disc-shaped region known as the Kuiper Belt. This is the realm of icy worlds, a frozen archive of the solar system's earliest days, home to dwarf planets like Pluto and thousands of smaller objects. For years, our models predicted that this population of icy bodies should continue in a relatively steady, gradual distribution, slowly thinning out as we move further from the Sun. But that's not what we see. Instead, at a distance of about 50 astronomical units, that's 50 times the distance from the Earth to the Sun, the number of detectable Kuiper Belt objects doesn't gently fade away, it plummets. It's as if someone built a cosmic wall, a sudden and dramatic drop-off that astronomers have nicknamed the Kuiper Cliff. This isn't just a minor statistical blip, it's a glaring anomaly that contradicts our basic understanding of how the solar system formed and evolved. If the original protoplanetary disk of material that swirled around our young sun simply ended at this point, we might expect such a cliff, but our models strongly suggest the disk extended much, much farther out. So where did all the objects beyond this point go? Their apparent absence is a profound puzzle, a silent boundary that seems to defy gravity and orbital dynamics. It's as if we're looking at a vast field of rocks that suddenly and inexplicably ends at a straight line, and we're left scratching our heads, wondering what could have possibly swept it so clean. The most thrilling and headline-grabbing hypothesis is that the Kuiper Cliff is the gravitational signature of an unseen world, a massive perturbing body whose influence has cleared out this region of space. This idea is a direct extension of the search for the hypothetical planet 9. The proposed planet, a world perhaps 5 to 10 times the mass of Earth on a highly elongated orbit hundreds of times farther from the Sun than we are, would have the gravitational muscle to significantly disrupt the orbits of smaller Kuiper Belt objects. As it travels along its immense multi-thousand-year path around the Sun, its gravity would act like a cosmic shepherd, either flinging objects inward toward the solar system, ejecting them into interstellar space entirely, or shepherding them into orbits that are tilted and clustered in ways we wouldn't otherwise expect. The Kuiper Cliff could represent the inner edge of its domain, the point where its gravitational influence becomes so dominant that it has effectively vacuumed the area, leaving behind this stark and telling emptiness. But an unseen planet isn't the only possible sculptor of this distant frontier. Another compelling theory reaches even further back in time, to the solar system's most chaotic and violent era. Perhaps the Kuiper Cliff is not the work of a modern-day giant, but a fossilized scar from a catastrophic event billions of years ago. Early in the solar system's history, the orbits of the giant planets are believed to have shifted in a period known as the Nice Model, a grand gravitational dance that would have sent immense ripples through the Kuiper Belt. During this turmoil, a close gravitational encounter with a passing star in the Sun's birth cluster could have stripped away a huge portion of the outer disk. Or perhaps the early solar system once contained a fifth giant planet, an ice giant like Uranus or Neptune that was gravitationally ejected by Jupiter, its departure violently scattering the primordial Kuiper Belt and carving out this abrupt boundary in the process. In this scenario, the cliff is a silent monument to a dramatic event that forever altered the architecture of our solar system, a ghostly imprint of a world that was lost. Resolving this mystery requires us to do what astronomers do best: look deeper and map more. The key to unlocking the secret of the Kuiper Cliff lies in discovering more of the extremely distant and faint objects that reside there. This is the primary mission of next-generation sky surveys, most notably the Vera-C, Rubin Observatory and its Legacy Survey of Space and Time, or LSST. With its enormous mirror and gigantic digital camera, this observatory will conduct a relentless, decade-long movie of the entire southern sky, night after night. It is designed to detect the faint, slow-moving pinpricks of light that are these distant Kuiper belt objects with unparalleled sensitivity. By discovering hundreds or even thousands of new trans-Neptunian objects and precisely plotting their orbits, the LSST will provide a rich, detailed census of the outer solar system. The specific patterns and clusters within those orbits will serve as a forensic record, allowing scientists to run sophisticated simulations and determine which gravitational influence, be it a distant planet or a past dynamical event, best explains the mysterious cliff we observe. This isn't just an academic exercise, it's a fundamental inquiry into our own origins. The Kuiper Belt is a deep freeze preservation of the pristine building blocks that never coalesced into a planet. By understanding its true structure and history, we are essentially reading the opening chapters of the solar system's biography, learning how our planetary family was assembled and what dramatic events shaped its current form. The Kuiper Cliff is a stark reminder that even in our own celestial neighborhood, there are still profound secrets waiting to be uncovered, hidden forces that have sculpted the edges of the sun's influence and which may yet point the way to worlds still unknown. Now let's turn our gaze from the distant, frozen edges of the solar system back to our own planet's deepest past, where we encounter a mystery that challenges our understanding of Earth's very origins. This is the faint young sun paradox, a puzzle that pits the unwavering laws of stellar physics against the clear geological evidence written in stone. Here's the conundrum. Based on our well-established models of how stars like our sun evolve, we know that billions of years ago, when life was first emerging on Earth, our sun was significantly dimmer, about 30% less luminous than it is today. Stars like ours slowly brighten as they age, burning through their hydrogen fuel. A 30% reduction in solar output would have been more than enough to turn our planet into a global snowball, a frozen wasteland with average temperatures far below the freezing point of water. And yet, the geological record tells a completely different and much warmer story. The ancient rocks from the Archean Eon, some 3 to 4 billion years old, show unmistakable signs of flowing water. Riverbeds, sedimentary deposits, and minerals that can only form in liquid water. Even more strikingly, there is compelling evidence for life itself, in the form of microbial fossils, thriving in what by all rights should have been a deep planetary freeze. So how did early Earth stay warm enough for rivers to flow and life to begin under the light of a faint young sun? Unraveling this paradox forces us to consider the powerful and complex role of our planet's atmosphere as a cosmic thermostat. The most widely accepted solution points to a very different ancient air, one choked with far higher concentrations of potent greenhouse gases than we have today. In a dimmer solar system, a supercharged greenhouse effect would have been essential to trap enough heat to keep the planet habitable. The prime suspect is carbon dioxide. If the early Earth had an atmosphere with 10 to 20 times more CO2 than current levels, it could easily have provided the necessary insulation. However, some climate models suggest that even extremely high CO2 levels might not have been sufficient on their own, leading scientists to propose an even more powerful helper, methane. Methane is a tremendously effective greenhouse gas, and it could have been produced in vast quantities by the earliest methane-producing microbes, known as methanogens, which may have dominated the ecosystems of the young planet. A combination of these two gases creating a thick, heat-trapping blanket is a compelling answer to the paradox, but the atmosphere's composition isn't the only factor in this planetary temperature equation. Another critical piece of the puzzle is Earth's albedo, its reflectivity. A brighter, more reflective planet bounces more sunlight back into space, cooling itself down. Today, our planet's albedo is significantly influenced by clouds and ice caps. The early Earth, however, might have been a much darker place, with less landmass exposed above the oceans and continents covered in darker, blackish volcanic rock instead of light-colored granite. The planet would have absorbed more of the sun's precious weak light. Furthermore, with fewer cloud-seeding particles like those produced by modern plants, cloud cover might have been thinner and less reflective. This darker world would have been a more efficient absorber of solar energy, helping to compensate for the sun's faintness. The implications of solving the faint young sun paradox extend far beyond a chapter in our own planetary history. It fundamentally shapes how we search for life elsewhere in the galaxy. As we point our telescopes at exoplanets orbiting other stars, we are essentially looking at versions of Earth at different stages of its life. Many of the most promising habitable zone planets we find orbit red dwarf stars, which are much cooler and dimmer than our Sun. Understanding how a planet can remain warm and wet under a faint sun is absolutely critical to assessing its true potential for harboring life. It teaches us that a planet's habitability is not just a simple function of its distance from its star, but a delicate and dynamic balance between stellar luminosity, atmospheric chemistry, and surface geology. This paradox reminds us that sometimes the most profound cosmic mysteries are the ones right beneath our feet, and solving them provides the key to unlocking the secrets of worlds light years away. But if you thought the faint young sun paradox presented a long-term climate puzzle, prepare to confront a mystery that unfolds in real time, a searing enigma that lies at the very heart of our solar system's relationship with its parent star. We are talking about one of the most enduring and counterintuitive puzzles in all of solar physics, the mystery of the solar corona. Here is the problem in its most basic and baffling form. If you were to stick a thermometer into the visible surface of the sun, the photosphere, it would read a scorching 5,500 degrees Celsius. That's hot enough to vaporize any known material, but if you then moved that thermometer just a few thousand kilometers upward, into the sun's wispy outer atmosphere, the corona, the temperature doesn't drop off as any sane person would expect. Instead, it soars, skyrocketing to an unimaginable 1 to 2 million degrees Celsius. It is the ultimate cosmic inversion, a place where the atmosphere is hundreds of times hotter than the surface below, a violation of the most fundamental principles of thermodynamics, which state that heat flows from hotter to cooler regions, not the other way around. It is as if you walked away from a blazing fire and instead of feeling cooler, you were instantly engulfed in flames orders of magnitude more intense. This bizarre heating has profound consequences that we can actually see during a total solar eclipse. When the moon perfectly blocks the brilliant disk of the photosphere, the ethereal, pearly white corona is revealed, stretching millions of kilometers into space. This beautiful, delicate glow is not reflected light. It is the corona itself, superheated to the point where it emits its own intense X-ray radiation. For decades, the mechanism that powers this incredible furnace has been the subject of intense debate and brilliant theorizing, with several compelling candidates vying for the title of the sun's primary heating engine. The first major suspect is a process called magnetic reconnection. The Sun is not a bland, static ball of gas. It is a churning, dynamic body laced with a powerful and incredibly complex magnetic field. These magnetic field lines are constantly being twisted, stretched, and tangled by the Sun's rotation and the convection currents boiling up from its interior. Sometimes these strained field lines can snap, breaking and reconnecting with other lines in a configuration that releases a colossal amount of stored magnetic energy. This explosive event is like uncrossing and then suddenly releasing a twisted rubber band, and it can inject enormous amounts of energy directly into the corona, heating the plasma to those multimillion-degree temperatures in localized bursts. A second, closely related theory proposes that the corona is being heated by a constant barrage of tiny, ubiquitous explosions known as nanoflares. Imagine the massive solar flares we sometimes see, which can release energy equivalent to millions of hydrogen bombs. Now, imagine a version of that event 1 billion times smaller, but happening everywhere all the time. The idea is that the Sun's magnetic field is in a perpetual state of nanoscale instability, with countless minuscule reconnection events continuously popping off like cosmic popcorn. While a single nanoflare is too small for us to detect individually, their collective effect could provide a steady, uniform heat source that keeps the entire corona simmering at its incredible temperature. The third leading theory takes a different approach, suggesting that the energy is delivered not through explosive reconnection, but through waves. The Sun's convective surface is a roiling, violent place, and it constantly generates powerful waves, specifically magnetic waves called Alfvén waves, that travel upward along the magnetic field lines, much like a wave traveling along a shaken rope. As these waves climb into the less dense corona, they can grow in amplitude and eventually break, like an ocean wave crashing on a shore, dumping all of their vibrational energy into the surrounding plasma and heating it up. It would be a more continuous and rhythmic heating process compared to the violent bursts of reconnection. For years, we could only observe the corona from a distance, making it incredibly difficult to distinguish between these theories. That all changed with the launch of NASA's Parker Solar Probe, a mission of almost unbelievable audacity. This robotic spacecraft is on a 7-year mission to literally touch the Sun, flying through the corona itself in a series of ever closer orbits, protected by a revolutionary heat shield that must withstand temperatures that would vaporize any other spacecraft. Parker is our first in situ detective, flying directly into the crime scene to gather forensic evidence. It is measuring the magnetic fields, sampling the solar wind particles, and feeling the Alfvén waves with its own sensors. The data it is sending back is already revolutionizing our understanding, providing the first direct measurements of the processes that might be solving this 80-year-old mystery. And it appears the answer may not be one single mechanism, but a complex combination of all three. Understanding this isn't just an academic exercise, it is a matter of practical, down-to-earth importance. The superheated corona is the source of the solar wind, a constant supersonic stream of charged particles that blows out in all directions, bathing the entire solar system. The dynamics of the corona directly influence the speed and density of this wind. Furthermore, the most violent coronal events like massive flares and coronal mass ejections are born from the same twisted magnetic energy that heats the corona. When these eruptions are directed at Earth, they can create devastatingly beautiful auroras, but they can also wreak havoc on our technology, inducing powerful electrical currents in power grids that can lead to widespread blackouts, frying satellite electronics, and disrupting global communication and GPS systems. By finally cracking the code of coronal heating, we get much closer to accurately predicting this space weather. allowing us to shield critical infrastructure and protect our technologically dependent society from the sun's unpredictable temper. This ongoing investigation into our own star's atmosphere provides the ultimate case study in stellar physics, a template we can use to understand the billions of other stars lighting up the cosmos. Of all the tantalizing clues in our search for life beyond Earth, few are as provocative and as frustratingly ambiguous as the case of the Martian methane. Imagine a scenario where our most sophisticated robotic laboratories on the red planet, after years of sniffing the thin, cold air, suddenly detect a whiff of a specific gas, one that on our own planet is overwhelmingly produced by living organisms. It would be a moment of electrifying promise, a potential whisper of biology on a dead world. This is precisely the situation we find ourselves in with Mars, a planetary detective story where the prime suspect is a simple molecule, CH4. The Curiosity rover, tirelessly exploring Gale Crater, has repeatedly recorded these brief, mysterious spikes of methane in the atmosphere. But in a twist that defines the challenge of interplanetary science, the European Space Agency's Trace gas orbiter, circling high above the planet, has often scanned the same regions at the same time and found nothing. This bizarre inconsistency isn't a sign that the instruments are broken. It's the heart of the mystery itself, pointing to a source that is not only hidden but also startlingly ephemeral, releasing its secrets in fleeting, unpredictable puffs that vanish almost as soon as they appear. So why is this particular gas such a big deal on Earth? The vast majority of atmospheric methane is biological in origin. It's belched by cows, released by decomposing plants in wetlands, and leaked from natural gas deposits formed from ancient organic matter. It's a signature of metabolism, a waste product of countless microbes known as methanogens that thrive in oxygen-free environments like the guts of animals or deep underground. Finding methane on Mars immediately opens the breathtaking possibility that similar, primitive microbial life could exist there right now, hidden away in aquifers deep beneath the frozen, radiation-scoured surface. This is the astrobiological dream scenario, a subsurface biosphere on Mars, a testament to the tenacity of life, surviving in isolated pockets of liquid water, metabolizing chemicals and producing methane as a byproduct. It's a compelling narrative, one that would fundamentally reshape our understanding of life's prevalence in the cosmos. But the universe rarely makes things so simple for us. There is an equally compelling and entirely non-biological explanation for this gas. Mars is a geologically active world in its own right, and a process called serpentinization could be the culprit. This is a chemical reaction that occurs when certain minerals, like olivine, come into contact with water in a low-oxygen environment. The reaction produces minerals called serpentines, hence the name, and as a byproduct, it can also release methane and hydrogen gas. This means that the methane we detect could simply be the result of ancient water-rock interactions, a testament to Mars's wetter past rather than its living present. Another abiotic theory involves the slow breakdown of ancient organic material delivered to Mars by meteorites over billions of years. This material, irradiated by the sun and without an ozone layer to protect it, could be slowly releasing methane as it weathers away. The challenge for scientists is that from hundreds of millions of miles away, the methane molecule itself looks identical, whether it was made by a microbe or a rock. This is where the plot thickens into a truly fascinating scientific puzzle. The key to distinguishing between a biological and a geological source may lie not in the methane itself, but in the specific type of carbon atom it contains. Carbon comes in different forms or isotopes. The most common is carbon-12, but a heavier, less common version is carbon-13. life on Earth strongly prefers to use the lighter carbon-12 isotope because it's easier to process. As a result, biological methane is significantly enriched in carbon-12 and depleted in the heavier carbon-13. If we could accurately measure the isotopic ratio of the Martian methane, if we could find that it is also light, it would be the strongest evidence yet that we are detecting a product of biology. The Curiosity rover has the tools to make these measurements, but the transient nature of the methane spikes makes it incredibly difficult. The gas appears and disperses so quickly that by the time the rover's instruments are ready to perform a detailed isotopic analysis, the evidence has often vanished into the thin Martian air. This is why the mystery of Martian methane is a driving force behind the next generation of robotic exploration. Future missions are being designed not just to sniff the air, but to dig far deeper. The concept is to go straight to the source. Imagine a rover equipped with a drill capable of reaching meters, not just centimeters, below the surface, beyond the reach of the destructive surface radiation that would sterilize any near-surface life. Such a mission could retrieve samples from deep underground, from layers where liquid water might still persist, and analyze them in situ for signs of microbial activity or the chemical fingerprints of serpentinization. Other proposed missions include specialized landers whose sole purpose would be to monitor atmospheric methane continuously from a fixed location, creating a long-term weather station for this mysterious gas to finally catch it in the act and trace its origin point. Solving this puzzle is about more than just checking a box on a scientific checklist. It is the essential next step in the search for extraterrestrial life. It teaches us how to look, what to look for, and how to interpret the most ambiguous of signals. The answer, whether it points to a living Mars or a fascinatingly complex geological one, will provide the definitive playbook for how we investigate the countless other worlds in our galaxy that may hold similar secrets. But if you thought the search for life on Mars was a complex detective story, then the saga of Venusian phosphine is a full-blown scientific thriller, a dramatic roller coaster of discovery, controversy, and the tantalizing possibility that we may have been looking for biology on the wrong planet all along. The story begins not with a rover on the ground, but with a powerful radio telescope pointed at our closest planetary neighbor. In September 2020, a team of astronomers made a stunning announcement. They had detected the spectral signature of phosphine gas in the temperate upper cloud decks of Venus. On its own, that might not sound like headline news, but the context is everything. On Earth, phosphine is a gas that is unequivocally associated with life. It's manufactured industrially, yes, but in nature, it is produced by anaerobic microorganisms, microbes that thrive in oxygen-free environments like swamps, landfills, and even the guts of animals like penguins. There are no known non-biological processes on our planet that can create phosphine in significant quantities. Finding it on Venus was like detecting the smell of freshly baked bread emanating from a kitchen we had long believed to be abandoned and sterile. It was a hint, a whisper, that something truly extraordinary might be happening 50 kilometers above that hellish surface. The location of this signal is absolutely critical to why it caused such a stir. The surface of Venus is a textbook example of a hostile environment, a crushing, scorching hellscape with pressures 92 times that of Earth and temperatures hot enough to melt lead. It is the last place anyone would look for life, but up in the cloud layers between 48 and 60 kilometers in altitude, the environment is surprisingly almost Earth-like. The temperature and pressure in this aerial zone are remarkably similar to those on our own planet's surface. The clouds aren't made of water vapor like ours, but of droplets of sulfuric acid, creating a highly corrosive and extremely dry environment. For decades, a small but passionate group of scientists had theorized that this unique niche could, in theory, serve as a habitat for extremophile microbes. These wouldn't be surface-dwelling organisms, they would be aerial life forms floating in the droplets, perhaps with a biochemistry built to withstand the acidic conditions. The detection of phosphine was the first piece of hard data that suggested this wild theory might not be so wild after all. However, in science, every extraordinary claim must face the gauntlet of extraordinary scrutiny, and the phosphine detection was immediately met with intense debate. Other teams of researchers rushed to reanalyze the data from other telescopes, and many failed to confirm the finding. The central issue lies in the immense difficulty of the measurement itself. Picking out the faint spectral fingerprint of a single molecule in the atmosphere of another planet is like trying to identify a specific person's whisper in a roaring stadium crowd. The signal is incredibly weak and can easily be confused with other, more common gases like sulfur dioxide. Critics argued that the team might have misidentified the signal or underestimated the background interference. Furthermore, other scientists began proposing alternative, abiotic pathways for phosphine production on Venus. Could intense volcanic activity, lightning strikes, or even meteorites delivering phosphorus-rich minerals to the atmosphere create the gas without any need for biology? The problem is that based on our current understanding of Venus's chemistry, all of these non-biological processes seem far too inefficient to produce the amount of phosphine that was initially reported. The very difficulty of explaining the gas through geology is what keeps the biological hypothesis alive. This fierce controversy perfectly highlights the limitations of remote sensing and the absolute necessity of in situ investigation. We can only learn so much by staring at Venus from hundreds of millions of miles away. To solve this mystery, we need to go there. We need to sample the atmosphere directly. This is the driving force behind a new wave of proposed missions to our neglected twin. NASA Da Vinci I+ mission, for example, is designed to be a true atmospheric probe. It won't land on the surface. Instead, it will plunge through the Venusian atmosphere for about an hour, sampling the air continuously during its descent. Its sophisticated instruments will be able to measure not only the presence of phosphine, but also its concentration at different altitudes and, crucially, its isotopic composition, a potential fingerprint that could distinguish between a biological and a geological origin. Other concepts envision balloons or flying craft that could navigate the cloud decks for weeks or months, acting as mobile laboratories to hunt for signs of life in this alien aerial ocean. The phosphine saga, regardless of its ultimate outcome, has already achieved something profoundly important. It has revitalized Venus exploration. For decades, Mars has been the darling of the planetary science community, while Venus was often seen as a fascinating but terminal case study in a runaway greenhouse effect. This one puzzling observation has reminded everyone that Venus is a dynamic, complex world with secrets of its own. It is Earth's twin in size and mass, yet it evolved down a dramatically different path. Understanding why is essential to understanding what makes a planet habitable, both in our solar system and around other stars. The possibility of life in the clouds of Venus forces us to expand our imagination of what a habitable environment can be. Life may not require a gentle, watery world with a solid surface. It might thrive in the most unexpected places, floating in acidic clouds under a perpetual overcast sky. This single mystery has reignited our curiosity about our nearest planetary neighbor, proving that sometimes the most exciting discoveries are waiting not in the farthest reaches of the cosmos, but right next door, challenging our assumptions and inviting us to look again. Venture now to the very edge of the Sun's dominion. to a place so distant and dim that it exists more as a ghostly concept in our celestial maps than a region we can truly see. This is the Oort Cloud, the solar system's final frontier, a vast and hypothetical spherical shell of icy planetesimals that marks the absolute boundary of our star's gravitational influence. To grasp its scale, consider the journey of the Voyager probes, our fastest and farthest flung spacecraft. It took Voyager 1 over 4 decades to reach interstellar space, having traveled well over 14 billion miles. Yet, even at that staggering distance, it has not yet reached the Oort Cloud's inner edge, and it won't for another 300 years. To fully pass through this frozen realm would take Voyager tens of thousands of years, a timescale that humbles all human ambition and frames the Oort Cloud not as a destination, but as a monument to the sheer, incomprehensible size of our own cosmic backyard. We have never directly observed this cloud, and with our current technology, we likely never will. Its existence is a brilliant piece of cosmic deduction, first proposed by the Dutch astronomer Jan Oort in 1950. He was trying to solve a puzzle. Where did the long-period comets, those spectacular visitors that take thousands or even millions of years to complete a single orbit, come from? Their orbits were not confined to the flat plane of the solar system like the planets. They arrived from all directions, suggesting a spherical source far beyond everything else we knew. Oort theorized a vast reservoir of icy remnants, the leftover building blocks from the solar system's formation that were never incorporated into planets. These frozen bodies, he reasoned, were occasionally nudged from their stable orbits by the gravitational influence of passing stars or the tidal pull of the Milky Way itself, sending them on a long fall inward toward the Sun, where we eventually see them light up as comets. This theoretical cloud is thought to be composed of trillions of icy objects, a mix of frozen water, ammonia, methane, and rock, each a pristine time capsule from the dawn of our planetary system. They are the original, unprocessed materials that swirled around our infant sun 4.5 billion years ago, preserved in the deep freeze of interstellar space. Studying the composition of comets that originate from the Oort Cloud as they blaze through our inner solar system gives us our only glimpse into the chemical recipe that built our worlds. These comets may have even been the delivery vehicles that brought water and the organic compounds essential for life to the early Earth, making the Oort Cloud not just a distant curiosity, but a potential player in our own origin story. The immense distance of this cloud also makes it a sensitive gauge for the history of our galactic neighborhood. The orbits of these trillions of objects are delicately balanced, easily perturbed by even the slightest external force. A star passing within a few light years of our solar system, a relatively common event over billions of years, would send gravitational ripples through the Oort Cloud, scattering countless comets and potentially hurling a shower of them into the inner solar system. Some scientists have even speculated that such stellar flybys could be linked to mass extinction events on Earth, a reminder that the dangers to life on our planet may not always come from within, but from the gentle, unseen tugs of stars passing in the galactic night. For now and for the foreseeable future, the Oort Cloud remains a realm of pure inference, a testament to the power of human reason to map the unseen. We cannot send probes to it, and our telescopes are powerless to spot its dark, frozen constituents against the blackness of space. It is the ultimate frontier of our solar system, the final gravitational tether that connects us to the Sun before the true emptiness of the interstellar void begins. Its very existence challenges our perception of where our system ends and the rest of the galaxy begins, a blurred and distant borderland that holds the deepest secrets of our beginning and hints at the subtle influences that have shaped our cosmic journey. After exploring the tangible, albeit mysterious, boundaries of our own solar system in the Oort Cloud, we now take the most profound leap imaginable, venturing beyond the very concept of a single universe to contemplate the ultimate cosmic mystery, the multiverse. This is not merely an idea about other planets or other galaxies, but about other entire realities, complete with their own space, time, and perhaps even their own unique laws of physics. The multiverse hypothesis proposes that our universe, with its hundreds of billions of galaxies and everything we will ever know, might be just one single bubble in a vast, frothing cosmic ocean of universes, an infinite ensemble of realities collectively known as the multiverse. This concept pushes the boundaries of cosmology, physics, and philosophy further than they have ever been pushed before, forcing us to confront the true meaning of existence itself. The scientific basis for this staggering idea doesn't spring from science fiction, but from the most successful and rigorous theories in modern physics. One of the strongest pillars comes from our leading theory of the universe's origin, cosmic inflation. This theory suggests that in the first fraction of a second after the Big Bang, space-time itself expanded at an exponential rate, smoothing and flattening our observable universe. But many versions of inflation suggest this process may not have been a one-time event. Instead, it could be eternal, ongoing in a much larger meta-universe. In this eternal inflation, quantum fluctuations could cause tiny pockets of spacetime to stop inflating and pinch off to form their own separate bubble universes, each with the potential for different initial conditions and physical properties. Our entire cosmos, in this view, is just one such bubble among an infinite number of others in an eternally inflating background. Another compelling path to the multiverse emerges from the depths of string theory, a leading candidate for a theory of everything that aims to unite gravity with quantum mechanics. String theory proposes that the fundamental constituents of reality are tiny, vibrating strings. However, for the math to work, it requires extra spatial dimensions beyond the three we experience. The way these extra dimensions are compactified or curled up determines the physical laws and constants of a universe, such as the strength of gravity or the mass of an electron. The problem, or perhaps the feature, is that string theory allows for a colossal number of possible ways for this compaction to happen, perhaps 10 to the 500 different ways. This leads to the concept of the string theory landscape, a vast, abstract terrain of possible universes, each with its own unique set of physical laws. In this framework, we simply happen to live in one universe out of a near-infinite array of possibilities, where the constants are perfectly tuned to allow for the formation of galaxies, stars, planets, and life as we know it. This notion of fine-tuning is perhaps the most powerful motivator for taking the multiverse idea seriously. Physicists have long been perplexed by the fact that many of the fundamental constants of nature seem perfectly and precariously calibrated for life. If the strength of the strong nuclear force were even slightly different, stars might not form. If the cosmological constant were a tiny bit larger, the universe would have ripped itself apart before galaxies could form. The probability of all these numbers lining up so perfectly by random chance in a single universe seems astronomically low. The multiverse offers a compelling explanation. If there are an infinite number of universes with different constants, then it is no surprise that we find ourselves in one of the rare, life-permitting ones. We are, in a sense, the inevitable outcome of a cosmic lottery with an infinite number of tickets. Yet this grand vision comes with a profound and, to some, a deeply troubling caveat: the problem of testability. By its very definition, these other universes would exist in domains completely separate from our own, with no possible exchange of information, energy, or matter. If something is fundamentally untestable and unobservable, can it truly be considered a scientific theory, or does it cross the line into the realm of metaphysics and philosophy? This is the central debate that rages within the scientific community. Proponents argue that the multiverse is a natural, and in some cases unavoidable, prediction of our best physical theories like inflation and string theory. They suggest that indirect evidence could someday be found, perhaps in the form of a peculiar pattern in the cosmic microwave background that could be interpreted as a bruise from a collision with another universe bubble in the distant past. Skeptics, however, maintain that without any conceivable way to falsify the idea, it resides outside the boundaries of science. They worry that accepting an infinite number of unobservable universes to explain the features of our own is a form of philosophical surrender, effectively ending the search for a deeper, more elegant theory that could explain our universe's fine-tuning from first principles. They argue that we risk making science itself untestable if we invoke an infinite number of invisible worlds to explain the one we can see. This tension lies at the very heart of the scientific method, challenging us to define where the line is between a bold scientific prediction and an untestable philosophical speculation. Ultimately, the multiverse hypothesis, whether it ever achieves the status of confirmed theory or remains a provocative thought experiment, serves a profound purpose. It is the final frontier of human curiosity, a concept that challenges our deepest assumptions about reality and our place within it. It forces us to relinquish the comforting idea that our universe is all there is, and to consider the breathtaking possibility that everything we know is just a single page in an infinite cosmic library. This idea doesn't diminish our significance. Instead, it expands the stage of existence to an almost unimaginable scale, providing a fittingly monumental and humbling conclusion to our journey through the cosmos's greatest mysteries. As we stand back and survey the incredible landscape of cosmic mysteries we've just traversed, from the invisible grip of dark matter shaping galaxies to the mind-bending possibility of a multiverse, a powerful and unifying theme begins to crystallize. Each of these 30 enigmas, in its own unique way, represents a vibrant frontier, a boundary line on the map of human knowledge where our relentless curiosity crashes into the hard limits of what we currently understand. This isn't a barrier that stops us, it's a horizon that invites us forward. These profound puzzles act as the ultimate catalysts for progress, forcing collaboration between astrophysicists and particle accelerator engineers, between philosophers and computer scientists, between theorists huddled over equations and engineers designing unimaginably sensitive instruments. The quest to detect a gravitational wave or to image a black hole's shadow doesn't just happen in one lab. It requires a global network of minds and technology, a testament to what we can achieve when we focus our collective intellect on a shared grand challenge. This pursuit of the unknown does far more than just satisfy our intellectual hunger. It sparks a cycle of innovation that reverberates back into our daily lives in the most tangible ways. The need to peer deeper into the cosmos than ever before drove the development of the charge-coupled device, the heart of every digital camera and smartphone. The algorithms created to sift through the cosmic noise of telescope data are now used to diagnose diseases and manage global financial systems. Our struggle to understand the quantum weirdness of particles has given us the entire field of quantum computing, promising a revolution in processing power. The search for dark matter and dark energy isn't just about figuring out what the universe is made of. It's a fundamental inquiry into the nature of reality that could, in time, unlock entirely new forms of energy or propulsion, technologies we can scarcely imagine today, but that might one day carry us to the stars. These mysteries are not abstract academic exercises. They are the forcing functions of our technological evolution, pushing our capabilities to their absolute limits and then beyond. Beyond the gadgets and the engineering marvels, these cosmic questions provide something even more precious: profound philosophical insight. Confronting the sheer scale of a cosmic void or the statistical improbability of our universe's fine-tuning forces a radical perspective shift. It humbles us, dismantling any lingering anthropocentric view that we are the central characters in a universe designed for us. Instead, we see ourselves as participants in a vast, dynamic, and often incomprehensible drama, a species gifted with just enough consciousness to look up and ask why. And how this perspective is not diminishing, it is liberating. It connects us to every human who has ever gazed at the night sky in wonder, from ancient storytellers tracing constellations to the scientists operating the James Webb Space Telescope. It's a reminder that the drive to explore is woven into the very fabric of our being, a defining trait of our species that has propelled us out of Africa and now yearns to reach beyond our solar system. By actively embracing these mysteries rather than fearing them, we honor that deepest spirit of exploration. We affirm that the value of a journey is not just in reaching a destination, but in the act of traveling itself, in the new questions we learn to ask, the new tools we are forced to invent, and the new ways of thinking we are compelled to adopt along the way. The universe, in its infinite complexity, is not a puzzle to be solved but a wonder to be continually explored, a constant source of awe that reminds us that no matter how much we learn, there will always be more wonders waiting just beyond the edge of our understanding. This collective engagement with the grandest questions of existence doesn't just belong to scientists in lab coats. It is a fundamental part of our shared human heritage, a story that invites every single one of us to be a participant in the greatest adventure there is. We have journeyed together through 30 of the universe's most profound and captivating enigmas, from the ghostly pull of dark matter to the staggering possibility of a multiverse. And what becomes undeniably clear is that our cosmos is a place of boundless wonder, designed to both humble and inspire. These are not mere gaps in a textbook. They are the vibrant, living frontiers of human understanding, where every answered question inevitably blossoms into a dozen new, even more fascinating ones. This perpetual cycle of discovery is what makes science the most thrilling adventure our species has ever undertaken, a journey with no final destination, but with infinite horizons to explore. It reminds us that the true value lies not just in the knowledge we gain, but in the perspective we earn along the way, a perspective that redefines our place in an astonishingly vast and mysterious reality. This grand expedition into the unknown does more than just satisfy our curiosity. It fundamentally shapes who we are and the future we are building. The relentless drive to comprehend the invisible forces holding galaxies together, or the nature of reality itself, has consistently been the engine of our greatest technological and philosophical revolutions. The tools we forge to peer into the depths of space inevitably find purpose in improving life here on Earth, from medical imaging to global communication networks. More importantly, this quest cultivates a crucial mindset of humility, resilience, and global cooperation. Confronting puzzles of this magnitude requires us to collaborate across cultures and disciplines, uniting humanity under the shared banner of discovery and reminding us that we are all crew members on the same small planet, adrift in a cosmic ocean of breathtaking beauty and mystery. As we bring this exploration to a close, I want to extend my deepest thanks to you for embarking on this intellectual voyage. Your curiosity is the lifeblood of this channel, and it's what makes creating this content so rewarding. The conversation doesn't have to end here. I am genuinely eager to hear which of these 30 mysteries captured your imagination the most. Was it the eerie silence of the Fermi paradox, the fleeting intrigue of ʻOumuamua, or the terrifying power of gamma-ray bursts? Let me know your thoughts in the comments below. I read every single one. If you enjoyed this deep dive into the cosmos's greatest secrets, please show your support by hitting that like button and subscribing to the channel. It truly helps us continue our mission to explore the universe's wonders together. Until our next adventure into the unknown, keep looking up, stay curious, and never let the world convince you that anything